Seminar of Civil Engineering Division IB on Seismic Design by ASCE 705, the basis of seismic design by BNBC 2017. Our keynote speaker on this topic is Dr. S.K. Ghosh, President S.K. Ghosh Associates, who is also Associates of ICC, International Code Council. You know, BNBC 2017 is waiting for approval. I think this is the peak time to know about something about BNBC 2017. When the delivery about the BNBC 2017 is from Dr. S.K. Ghosh, who is fully engaged to prepare the BNBC, then the session is very important to our professionals. All discussion, honorable discussions, our Raju team. Our main discussion is our engineer MD Nurul Huda, former chairman Raju, also ex-president of IEB. Another honorable discussion is Professor Dr. Rakib Hausan, Professor of Civil Engineering Department, Kuwait, and also the team member of working for Raju. Another honorable foreign discussion is Dr. Eric Mouset, team leader package S7 of URP, that means Urban Resilience Program of Raju. We are sorry for that. In our banner, Mr. Eric Mouset, a name spelling mistake, on doctorate, his doctorate of ICT, PhD on ICT. I am very sorry from our Civil Engineering Division IB as the Secretary of Civil Engineering Division. So thank you for the presence. We want to start the program after our ASCE prayer. We wait for our chief guest also. Till then, you are welcome at our session. Honorable discussion, Engineer MD Nurul Huda, Professor Dr. Engineer Rakib Hausan, Dr. Eric Mouset, and honorary guest, HGS IB, Engineer Bandhagan Manjur Moshed, is present at the stage. This seminar is presided by Engineer MD Habibur Rahman, Chairperson of Civil Engineering Division IB. I request our chairman to give me the permission to start the program. May I start, sir? Thank you to our chairperson. From our Civil Engineering Division, we welcome all of our honorable guests by flower bouquet. I request Mr. Engineer Munir, Engineer Oni, Engineer Nisa, and Engineer Mim to welcome all our honorable guests by flower bouquet. would like to request our AGS, Honorary General Secretary of IEB, Engineer Khandakar Manjur Morshed, to give his opening speech.
ধন্যবাদ প্রকৌশলী শেখ তাজুল ইসলাম তুহিন, সম্পাদক প্রকৌশল বিভাগ আইবি। প্রকৌশল বিভাগ ইঞ্জিনিয়ার্স ইনস্টিটিউশন বাংলাদেশের উদ্যোগে আজকের এই সেমিনার সিসমিক ডিজাইন বাই ASCE 705, দি বেসিক অফ সিসমিক ডিজাইন বাই DNBC 201 শীর্ষক সেমিনারের শ্রদ্ধেয় সভাপতি প্রকৌশলী মোহাম্মদ হাবিবুর রহমান, চেয়ারপারসন প্রকৌশল বিভাগ আইবি। আজকের অনুষ্ঠানের প্রধান অতিথি প্রকৌশলী মোহাম্মদ আব্দুল সবুর, প্রেসিডেন্ট ইনস্টিটিউশন অফ ইঞ্জিনিয়ার্স। আজকের অনুষ্ঠানের কিনোট স্পিকার ডক্টর SK ঘোষ, প্রেসিডেন্ট SK ঘোষ অ্যাসোসিয়েশন অফ ICC, ইন্টারন্যাশনাল পোর্ট কাউন্সিল অ্যান্ড মেম্বার আমেরিকান কংক্রিট ইনস্টিটিউট। আজকের অনুষ্ঠানের মূল আলোচক প্রকৌশলী মোহাম্মদ নুরুল হুদা, প্রাক্তন চেয়ারম্যান। অধ্যাপক ডক্টর প্রকৌশলী রাকিব আহসান, পুরকৌশল বিভাগ বুয়েট এবং মৌসেফ, টিম লিডার প্যাকেজ 7 অফ URP লাজুক RTI। উপস্থিত আমার সুধীর প্রকৌশলবৃন্দ, আইবির নির্বাহী কর্মকর্তাবৃন্দ, ঢাকা কেন্দ্রের কর্মকর্তাবৃন্দ, রাজুক থেকে আগত আমাদের বিভিন্ন প্রকৌশলীবৃন্দ, আমাদের এক্স প্রেসিডেন্ট প্রকৌশলী এবং স্বামীজীবন ভূঁইয়া স্যার সহ আমাদের রাজুকের কর্মকর্তাগণ এবং সাংবাদিক মিডিয়ার ভাই বোন সকলকে আসসালামু আলাইকুম। আমি প্রথমে শ্রদ্ধাভরে স্মরণ করছি সর্বকালের সর্বশ্রেষ্ঠ বাঙালি, জাতির জনক বঙ্গবন্ধু শেখ মুজিবুর রহমান, যিনি না হলে এই বাংলাদেশ হতো না। আর এই বাংলাদেশ না হলে আমরা প্রকৌশলী কৃষিবিদ চিকিৎসক হয়ে আজ এখানে আসতে পারতাম কিনা এই ব্যাপারে সন্দেহ। আমি আরো স্মরণ করছি সে সকল শহীদদের যাদেরকে 15ই আগস্টে নির্মমভাবে হত্যা করা হয়েছে। আমি আরো স্মরণ করছি 30 লক্ষ শহীদ ও 2 লক্ষ মা বোনদের ইজ্জতের বিনিময়ে যারা বাংলাদেশ স্বাধীন করেছে সে সকল বীর মুক্তিযোদ্ধাদের। এবং আমি আরো স্মরণ করছি আমাদের আইবির প্রতিষ্ঠা লগ্ন থেকে এ পর্যন্ত জব্বার সহ প্রকৌশলী জব্বার সহ যারা ইন্তেকাল করেছেন তাদের আত্মার মাগফিরাত কামনা করছি। আমি প্রথমে ধন্যবাদ জ্ঞাপন করছি সিভিল ইঞ্জিনিয়ারিং বিভাগকে। তারা একটা সুন্দর সেমিনার আয়োজন করেছে। যে সেমিনারে আমার জানা মতে বিশেষভাবে আমন্ত্রণ জানানো হয়েছে রাজুক ইন্ডাস্ট্রিয়াল প্রকৌশলীদের। এখানে আরো উপস্থিত আছেন আমার যতদূর মনে হয় উল্লেখযোগ্য সংখ্যক সম্মানিত স্ট্রাকচারাল ইঞ্জিনিয়ার, বিপিআরবির সাথে সংশ্লিষ্ট প্রফেশনাল ইঞ্জিনিয়ার, পিএইচ প্রাপ্ত সকলকে ধন্যবাদ জ্ঞাপন করছি। এরকম একটা হাইলি টেকনিক্যাল সেমিনারের আয়োজনের মাধ্যমে আইবিটি একটি প্রফেশনাল ইনস্টিটিউশন সেরকম পরিবেশ সৃষ্টি হয়েছে। এই জন্য আমি সিভিল ইঞ্জিনিয়ারিং সহ যারা এই সেমিনার আয়োজনের যারা মূল আয়োজক তাদেরকে আমি ধন্যবাদ জ্ঞাপন করছি। আজকের এই সেমিনারের মূল প্রবন্ধকা ডক্টর SK ঘোষ, উনি একজন আন্তর্জাতিক খ্যাতিসম্পন্ন প্রফেশনাল ইঞ্জিনিয়ার। তিনি SK ঘোষ অ্যাসোসিয়েশন প্রেসিডেন্ট, আবার SK ঘোষ অ্যাসোসিয়েশন কাজ করছে ইন্টারন্যাশনাল কোর্ট কাউন্সিল ICC অ্যাসোসিয়েশন হিসাবে। তিনি একাধারে আমেরিকান কংক্রিট ইনস্টিটিউটের ফেলো। এরকম একজন প্রতিষ্ঠা ব্যক্তি DNBC বাংলাদেশ ন্যাশনাল বিল্ডিং কোড 2017 নিয়ে কাজ করছেন। এই জন্য আমরা আইবির পক্ষ থেকে রাজুকে ধন্যবাদ জ্ঞাপন করছি এবং ডক্টর SK ঘোষের প্রতি কৃতজ্ঞতা জ্ঞাপন করছি। কেননা আজকে সবাই উপযোগী একটি সেমিনার। আপনারা জানেন যে কিছুদিন আগে আমাদের এফআর টাওয়ার সহ আমাদের যে চকবাজার ট্র্যাজেডি সেটা কিভাবে কি হয়েছে সেটা BNBC যদি থাকতো আজকে ঠিক মতো আমাদের প্রকৌশলীরা যে সমস্ত বা রাজুক যে সমস্ত জিনিস তৈরি করে দিয়েছিল আজকে যদি সেটা বাস্তবায়ন হয়ে থাকতো তাহলে মনে হয় আজকে এত বড় দুর্যোগ বাংলাদেশে হতো না। এই জন্য BNBC 2017 কোর্ট প্রস্তুতিতে যিনি ভূমিকা রেখেছেন তিনি BNBC 2017 উপর ভিত্তি করে সিসমিক ডিজাইনের উপর মূল প্রবন্ধ স্থাপন করছেন। এটি আমাদের ডিজাইন ইঞ্জিনিয়ারের জন্য খুবই সহায়ক বলে আমি মনে করি। অনুষ্ঠানের সম্মানিত আলোচক হিসাবে উপস্থিত আছেন আরবান রেজিডেন্স প্রোগ্রামার URP এর টিম লিডার মিস্টার এরিক মোসেফ। রাজুক ইতিমধ্যে বিল্ডিং এর প্ল্যান পাস করার প্রক্রিয়াটি অনলাইন প্রক্রিয়ার মাধ্যমে করার ব্যবস্থা করেছেন। মিস্টার এরিক এই অনলাইন প্রক্রিয়ার উপর টেকনিক্যাল সাপোর্ট দিয়েছেন। ইন্ডাস্ট্রিয়াল ইঞ্জিনিয়ারগণ এই ব্যাপারটিতে একটা দিক নির্দেশনা পালন করবেন। আমাদের মাঝে আলোচক হিসাবে রয়েছেন কুয়েটের অধ্যাপক ডক্টর রাকিব আহসান, যিনি এই টিমের সাথে একজন বিশেষজ্ঞ হিসেবে কাজ করছেন। ঢাকা শহরে বিল্ডিং ডিজাইনের বর্তমান সমস্যা ও ভবিষ্যতের সমাধানটা কি হবে তিনি জীবনে লেখা পরিবেশন করে জেনেছেন। তাই তার বাস্তব অভিজ্ঞতা থেকে সেমিনারে অংশগ্রহণকারীগণ অনেক কিছু জানতে পারবে। আপনারা তো জানেন যে ইনস্টিটিউশন অফ ইঞ্জিনিয়ার্স, ইনস্টিটিউট অফ আর্কিটেক্টস আমাদের যে কাজগুলো করছেন বিএনপিসি নিয়ে আমরা ইতিমধ্যে অনেকগুলো বৈঠক করেছি। আমরা আজকে গৃহ মন্ত্রণালয়ের সঙ্গে মন্ত্রীর সঙ্গে বৈঠক করেছি। সেখানে হয়তো আমরা কিছুদিনের মধ্যে আমরা যে একটা রিপোর্ট তৈরি করেছি, মতামত তৈরি করেছি, আমরা সেটা সেখানে জমা দেব। কাজেই আজকে যে সমস্ত সুপারিশমালা আমাদের মাধ্যমে আপনাদের মাধ্যমে আমাদের কাছে আসবে এগুলো আমরা সন্নিবেশন করে আমরা সরকারের উচ্চ পর্যায়ে পৌঁছিয়ে দিব, যাতে করে ভবিষ্যতে বাংলাদেশ একটি শক্তিশালী রাষ্ট্রে পরিণত হয়। যে সমস্ত বিল্ডিং আমরা করব একটি সুন্দর সিস্টেমের মাধ্যমে আমাদের করতে হবে, সেখানে সব ফ্যাসিলিটিগুলো রাখতে হবে। আমরা সবাই জানি বাংলাদেশ ভূমিকম্পন প্রবণ দেশ। ঢাকা শহর সহ সারা দেশে বিভিন্ন ধরনের বিল্ডিং তৈরি হচ্ছে। সকল এলাকার বিল্ডিংকে ভূমিকম্পের ঝুঁকি হতে নিরাপদে রাখতে ডিজাইনের সময় স্ট্রাকচারাল ইঞ্জিনিয়ারকে অবশ্যই ভূমিকা রাখবে। আইবি ইতিমধ্যে সকল পৌরসভা, আপনারা জানেন কিনা, সিটি কর্পোরেশন আইবির পক্ষ থেকে প্রতিনিধি হিসাবে প্রকৌশলে রাখার প্রস্তাব করেছে। তাদের সবাই বিএনপিসি এর সিস্টেমিক ডিজাইন অনুসরণ করে বিল্ডিংগুলোর প্রথম অনুমোদন দেবে। এ ব্যাপারে সর্বোচ্চ সতর্কতা অবলম্বন করা হবে বলে আইবি প্রত্যাশা করে। আমাদের দেশের ভবনগুলি মজবুত ও ভূমিকম্প সহনীয় হলে এই সেমিনারের সার্থকতা লাভ করবে। আমি আশা করব আজকে আমাদের সবাইকে ভালো লাগছে এবং আমি যেন আবার ধন্যবাদ জ্ঞাপন করছি। আপনারা আমাদের মাঝে কষ্ট করে এসেছেন, এই সমস্ত এই সেমিনারে আপনারা উপস্থিত রয়েছেন। আপনাদের মাধ্যমে আমাদের সুপারিশমালাগুলো আসবে, আপনারা লিখিত আকারে অথবা আপনারা কম্পিউটারের ইমেলের মাধ্যমে আমাদের পাঠিয়ে দিবেন, যাতে করে আমরা একটা শক্তিশালী বাংলাদেশ প্রতিষ্ঠিত করতে পারি। শেখ হাসিনার হাত ধরে আমরা বাংলাদেশকে এগিয়ে নিয়ে যাবো। বঙ্গবন্ধু কন্যা বাংলাদেশকে এগিয়ে নিয়ে যাচ্ছে, তারই ধারাবাহিকতা থাকার জন্য আইবি সদা প্রস্তুত। সকলকে ধন্যবাদ। জয় বাংলা, জয় বঙ্গবন্ধু, বাংলাদেশ চিরজীবী হোক।
প্রকৌশলী খন্দকার মঞ্জুর মোর্শেদ, সম্মানিত সাধারণ সম্পাদক আইবি, আমাদের মাঝে ইতিমধ্যে উপস্থিত হয়েছেন প্রকৌশলী ডক্টর সুলতান আহমেদ, চেয়ারম্যান রাজু। আমরা তাকে আমাদের এই সেমিনারে স্বাগত জানাচ্ছি। সবাই করতালির মাধ্যমে স্বাগত জানাচ্ছি ডক্টর সুলতান আহমেদ, চেয়ারম্যান রাজু। আমি প্রকৌশলী মনিরকে আমাদের অতিথিকে ফুল দিয়ে স্বাগত জানানোর জন্য অনুরোধ করছি। আজকের মূল প্রবন্ধকার ডক্টর এস.কে. ঘোষ তার জীবনী থেকে সংক্ষেপে পাঠ করবেন এবং আপনাদেরকে স্বাগত জানাবেন সিভিল ইঞ্জিনিয়ারিং ডিভিশনের ভাইস চেয়ারম্যান অধ্যাপক ডক্টর প্রকৌশলী মিজানুর রহমান।
বিসমিল্লাহিররহমানিররহিম। সিভিল ইঞ্জিনিয়ারিং ডিভিশন আইবি কর্তৃক আয়োজিত Seismic Design by ASCE 705, the basis of seismic design by BNPC 2017 শীর্ষ সেমিনারের সভাপতি প্রকৌশলী মোহাম্মদ হাবিবুর রহমান, চেয়ারম্যান প্রকৌশল বিভাগ আইবি। প্রধান অতিথি আইবির সম্মানিত প্রেসিডেন্ট ইঞ্জিনিয়ার মোহাম্মদ আব্দুস সবুর, আজকের মূল প্রবন্ধ উপস্থাপক ডক্টর এস.কে. ঘোষ, বিশেষ অতিথি হিসেবে উপস্থিত আছেন রাজুকের চেয়ারম্যান, সম্মানিত আলোচকবৃন্দ ডক্টর এরিক হোসেন, প্রফেসর ডক্টর রাকিব হাসান, প্রকৌশলী মোহাম্মদ নুরুল হুদা। উপস্থিত আছেন আইবির সম্মানিত সাধারণ সম্পাদক প্রকৌশলী খন্দকার মঞ্জুর মোর্শেদ, আইবির অন্যান্য নেতৃবৃন্দ। উপস্থিত আছেন আবার সম্মানিত শিক্ষক প্রফেসর শামীম জেড বসুরিয়া, আরও বিভিন্ন অর্গানাইজেশন থেকে যে সকল সম্মানিত প্রকৌশলীরা এখানে এসেছেন, সবাইকে আসসালামু আলাইকুম। আমি ডক্টর মোহাম্মদ মিজানুর রহমান, ভাইস চেয়ারম্যান প্রকৌশল বিভাগ আইবি। আপনাদের সবাইকে আজকের এই সেমিনারে স্বাগত জানাচ্ছি। আজকের এই সেমিনারের যে বিষয়বস্তু, আমরা যারা প্রফেশনাল ইঞ্জিনিয়ার, বিশেষ করে স্ট্রাকচারাল ইঞ্জিনিয়ার যারা এখানে রয়েছেন, তাদের জন্য আজকের বিষয়টি খুবই গুরুত্বপূর্ণ। একসময় আসলে আমাদের বিশ্বাস ছিল যে আমাদের দেশ ভূমিকম্পের এত ঝুঁকিতে আমরা নেই, কিন্তু আসলে ইদানিংকালে দেখা যাচ্ছে যে আমরা ভূমিকম্পের ঝুঁকির মধ্যে আছি এবং সেই কারণেই কিন্তু আমাদের বিগত দিনে বিশেষ করে 10-15 বছর ধরে আমাদের যেসব বিল্ডিং, টল বিল্ডিং বা হাই রাইজ বিল্ডিং যেগুলো আমরা বলি যে ডিজাইন হচ্ছে, সেগুলো কিন্তু আমাদের আর্থকোয়েক ডিজাইন ফলো করেই আপনার ডিজাইন করা হচ্ছে। আসলে ন্যাচারের সাথে তো আমরা যুদ্ধ করতে পারবো না, কারণ ন্যাচারের অনেক ডেভাস্টেটিং যে রূপগুলো আছে সেগুলো সঙ্গে আমাদের অনেকভাবে পরিচয় হয়। এর মধ্যে ভূমিকম্প, সুনামি, সাইক্লোন, এগুলোর সাথে আমাদের কোপ করে নিতে হবে। এগুলোকে আমরা হয়তো পরিপূর্ণভাবে জয় করতে পারবো না, কিন্তু আমাদের প্রস্তুত থাকতে হবে এবং যতটা কম ক্ষয়ক্ষতি এইসব প্রকৃতির যে ডেভাস্টেটিং রূপ আছে সেগুলো থেকে যেন হয়, সেই জন্যই কিন্তু আমাদের বিল্ডিংগুলো আমাদের এইভাবে ডিজাইন আমাদের করতে হবে। আর বিএনপিসিতে আসলে ASCE 705 2005-এর যে এডিশন, সেই এডিশন অ্যাডাপ্ট করে আসলে কোডগুলা সেখানে বিএনপিসিতে উল্লেখ করা হয়েছে, কিন্তু আমরা জানি যে এখন কিন্তু আরো অনেক 2016 সালেরও এডিশন এখন চলছে। এর মধ্যে যদি কোনো নতুন কিছু থাকে তাহলে সেগুলো আমাদের বিজ্ঞ যেই আলোচকরা আছেন এবং কিনোট স্পিকার আছেন সেগুলো হয়তো তারা আলোকপাত করবেন, যাতে আমাদের যারা প্রফেশনাল বা প্র্যাকটিসিং ইঞ্জিনিয়ার যারা আছেন তারা সেগুলো সম্পর্কে জানতে পারে। আমি এখন আমাদের আজকের যেই মূল প্রবন্ধ উপস্থাপক ডক্টর SK ঘোষ, ওনার আসলে বর্ণাঢ্য জীবনী, সেখান থেকে আমি খুব সংক্ষিপ্ত আকারে আমি কিছু উল্লেখ করতে চাই। ডক্টর সত্যেন্দ্র কুমার ঘোষ, উনি আসলে আমাদের সবার কাছে ডক্টর SK ঘোষ নামেই বেশি পরিচিত। 1945 সালে উনি ভারতে জন্মগ্রহণ করেন। ডক্টর ঘোষ 1966 সালে ইউনিভার্সিটি অফ ক্যালকাটা, ইন্ডিয়া থেকে সিভিল ইঞ্জিনিয়ারিং স্ট্রাকচারে উনি BSc ডিগ্রি অর্জন করেন। 1969 সালে ইউনিভার্সিটি অফ ওয়াটারলু, কানাডা থেকে সিভিল ইঞ্জিনিয়ারিং এ MSc এবং সেই একই ইউনিভার্সিটি থেকে 1972 সালে স্ট্রাকচারাল ইঞ্জিনিয়ারিং এ PhD ডিগ্রি অর্জন করেন। বর্তমানে ডক্টর SK ঘোষ প্রিকাস্ট প্রিস্টেস কংক্রিট ইনস্টিটিউট, শিকাগোর পোর্ট কনসালটেন্ট এবং SK ঘোষ অ্যাসোসিয়েটের প্রেসিডেন্ট হিসেবে কর্মরত আছেন। ডক্টর SK ঘোষ অনেক প্রফেশনাল যে অ্যাসোসিয়েশন আছে তার সদস্য, এর মধ্যে আমি উল্লেখযোগ্য কিছু উল্লেখ করছি। উনি আমেরিকান কংক্রিট ইনস্টিটিউটের মেম্বার, আমেরিকান সোসাইটি অফ সিভিল ইঞ্জিনিয়ার্সের ফেলো এবং স্ট্রাকচারাল ইঞ্জিনিয়ারিং ইনস্টিটিউট SEI এর ফেলো, মেম্বার ASCE 7 সিসমিক সাব কমিটি এবং আর্থকোয়েক ইঞ্জিনিয়ারিং রিসার্চ ইনস্টিটিউটের উনি সদস্য। প্রফেশনাল লাইফে যেহেতু উনি কনসালটেন্ট, ওনার উল্লেখযোগ্য কিছু কনসালটেন্সি অ্যাক্টিভিটি আমি এখানে উল্লেখ করছি। Dr. Ghosh served as a consultant on a number of significant projects dealing with deficiencies in existing concrete building, the seismic design of multi-story reinforced concrete buildings, and with compensation for column length changes in ultra high-rise concrete and steel concrete composite building. Dr. SK ঘোষের অনেক ইন্টারন্যাশনাল পাবলিকেশন রয়েছে, তার মধ্যে আপনার বই, তারপরে ম্যানুয়াল, কোড এবং হ্যান্ডবুকও রয়েছে। তার মধ্যে আমি উল্লেখযোগ্য কিছু উল্লেখ করতে চাই। 2007 সালে প্রিকাস্ট প্রিস্টেস কংক্রিট ইনস্টিটিউট PCI যেটা পাবলিশ করেন একটা ম্যানুয়াল, সিসমিক ডিজাইন অফ প্রিস্টেস প্রিকাস্ট কংক্রিট স্ট্রাকচার। এরপর একটা বই যেটা নাকি আপনার 2000 সালে ASCE থেকে পাবলিশড হয়, সিসমিক অ্যান্ড উইন্ড ডিজাইন অফ কংক্রিট বিল্ডিং 2000 IBC ASCE 798 and ACI 31899. 2002 সালে IBC হ্যান্ডবুক অন স্ট্রাকচারাল প্রভিশন এর উপরে যে হ্যান্ডবুক পাবলিশ হয়, উনি তার একজন co-author। ওনার আরো উল্লেখযোগ্য যে পাবলিকেশন তার মধ্যে আপনার ACI স্পেশাল পাবলিকেশন SP127 Earthquake Resistance Concrete Structure Inelastic Response and Design, এবং PC এর অনেক পাবলিকেশনে উনি এডিটর বা co-author হিসেবে উনি ছিলেন, এখনো আছেন। ডক্টর ঘোষ পৃথিবীর বিভিন্ন জায়গায় যে বড় বড় আপনার আর্টওয়ার্ক হয়েছে সেগুলোর উনি ইনভেস্টিগেশন করেছেন। তার কিছু কোন কোন আর্টওয়ার্ক সেগুলো আমি একটু উল্লেখ করতে চাই। মেক্সিকোর 1985 সালের যে আর্টওয়ার্ক, 1987 সালের লস অ্যাঞ্জেলেসের আর্টওয়ার্ক, 1995 সালের জাপানের কোবেতে যেই আর্টওয়ার্ক, তারপরে 1999 সালে তার্কিতে যে আর্টওয়ার্ক, 2001 সালে ইন্ডিয়ার ভুজে যে আর্টওয়ার্ক, 2005 সালে পাকিস্তানের কাশ্মীরিতে যে আর্টওয়ার্ক, 2010 সালে চিলির আর্টওয়ার্ক এবং 2011 সালে জাপানের যে আর্টওয়ার্ক হয়েছে সেই আর্টওয়ার্কের উনি পারফরমেন্স অফ কংক্রিট স্ট্রাকচারের ইনভেস্টিগেশন করেছেন। ওনার এই বর্ণাঢ্য জীবনে উনি অনেক অ্যাওয়ার্ড পেয়েছেন, আমি কিছু উল্লেখ করতে চাই। গভর্নমেন্ট অফ ইন্ডিয়া ন্যাশনাল স্কলারশিপ, ইঞ্জিনিয়ারিং কংগ্রেস প্রাইজ, দ্য ইনস্টিটিউট অফ ইঞ্জিনিয়ার্স ইন্ডিয়া, ACI স্ট্রাকচারাল রিসার্চ প্রাইজ, চার্লস সি জোলম্যান অ্যাওয়ার্ড, আর্থার জে বোস অ্যাওয়ার্ড অফ রেইনফোর্স কংক্রিট রিসার্চ কাউন্সিল, ACI জো ডাব্লিউ কেলি অ্যাওয়ার্ড, ওয়াল্টার পি মোর জুনিয়র অ্যাওয়ার্ড, লেসলি ডি মার্টিন অ্যাওয়ার্ড, চার্লস ফানকো অ্যাওয়ার্ড সহ অসংখ্য অ্যাওয়ার্ডে উনি ভূষিত হয়েছেন। ডক্টর SK ঘোষ ওনার অনেক ব্যস্ততা সত্ত্বেও আজকে আমাদের এখানে প্রেজেন্টেশন করতে সম্মতি হয়েছেন, এই জন্য সিভিল ইঞ্জিনিয়ারিং ডিভিশন আইবির পক্ষ থেকে আমি ওনাকে আন্তরিক ধন্যবাদ জানাচ্ছি এবং আমাদের কৃতজ্ঞতা প্রকাশ করছি। ওনার যে প্রেজেন্টেশন সেই প্রেজেন্টেশন থেকে আমাদের যারা আজকের এখানে প্রফেশনাল ইঞ্জিনিয়াররা উপস্থিত আছেন তারা সবাই আমি বিশ্বাস করি উপকৃত হবেন এবং আপনাদের যেই জ্ঞানের ভান্ডার সেই জ্ঞানের ভান্ডার অবশ্যই সমৃদ্ধ হবে বলে আমি বিশ্বাস করি। আমি সর্বশেষে উপস্থিত ইঞ্জিনিয়ারদেরকে ধন্যবাদ জানাচ্ছি আজকের এই সেমিনারে অংশগ্রহণ করার জন্য। আপনারা সবাই এই সেমিনার উপভোগ করবেন এই আশাবাদ ব্যক্ত করে আমার বক্তব্য শেষ করছি। সবাইকে ধন্যবাদ।
এ পর্যায়ে আমাদের মূল প্রবন্ধ উপস্থাপন করবেন ডক্টর SK ঘোষ। ওনার পরিচয় তো বললেনই, আমি আর বাড়াতে চাই না, শুধু আমরা একটা খুশির সংবাদ শুনলাম যে উনি বাইবর্ন, আমাদের জাতি ভাই বাঙালি, এই উপলক্ষে আমরা একটা হাততালি দিতে পারি। আর আমি দুঃখ প্রকাশ করছি যে আমাদের আজকে এতজন উপস্থিতি হবে, এতজনের আমি বুঝতে পারি নাই। আমাদের ফলে আসলে ধারণ ক্ষমতার চেয়ে বেশি আপনারা উপস্থিত হয়েছেন, এজন্য ধন্যবাদ জানাচ্ছি আপনাদেরকে। একটু কষ্ট করে যারা এখন সিট পানে দাঁড়িয়ে শুনতে হবে, আর হচ্ছে আমরা পরবর্তীতে যখন প্রফেশনালরা আসবেন আমাদের সেমিনারে আমরা চেষ্টা করব আইবি ওয়েডিয়ামে এই প্রোগ্রামটা করার। ধন্যবাদ সবাইকে। এবারে আসছেন ডক্টর SK ঘোষ।
We are competing today with the cricket match in World Cup. So my friend Shahid Alam and I coming in the car were discussing if anybody would show up. This is really incredible, and I am truly sorry that some of you have to stand. I put together kind of a long presentation, not realizing that it would start so late. So we'll see. I may skip some things. I don't know. Anyway, so it is really a nice opportunity to talk to you about a very important subject, and I will try to. Details are unavoidable in a talk like this. At the same time, I'll try to speak to the basics to the extent that it makes sense. The topic, as you know, is seismic design, specifically by ASCE 705. ASCE 7 is just the designation of the standard, as we call it. It is adopted by the International Building Code, which then forms the basis of all the legal codes in the US. So the seismic design provisions in this document are what are used in seismic design across the United States. The 05 edition of ASCE 7 is the basis of not the code that is in the picture, but 2017 BNBC that you have been hearing about. The 2006 edition that is in the picture, and that is the only one I had a hard copy of, was completed a long time ago. It's an outdated document by now. Is the 2017 BNBC based on ASCE 705 is significantly more advanced than the 2006 edition, and it seems to be absolutely essential that the 2017 edition get final government approval and start getting used in design. The ASCE 705 that you saw was the basis of 2006 edition of the International Building Code and 2009 edition of the International Building Code. Since then, we have had ASCE 710, which is the basis of 2012 and 2015 IBC. The International Building Code comes out regularly every 3 years, updated. And then we have ASCE 716 now. This is the current edition, although we are working on ASCE 722 and more than halfway through. The ASCE 716 that you see in the picture is the basis of 2018 IBC, which is the latest available, but 2021 IBC has been completed and will be available in a matter of months. The seismic design provisions are in one section of the IBC, section 1613, irrespective of what edition you look at, provided you don't go earlier than 2006. ASCE 705, again, ASCE 7, beginning in ASCE 705, the seismic provisions are in chapters 11 through 23. In 2017 BNBC, and I was talking to Dr. Akib sitting here, that the organization of BNBC is very tough. You have to deal with parts and chapters and so forth. Anyway, in BNBC 2017, the earthquake provisions are in section 2.5 in part 6, chapter 2 of the code. We need design load combinations for seismic design. Those are in section 2.7. And the seismic design that I will talk about is in Appendix C to part 6 of BNBC 17. It's slightly different from what is in the main body. Anyway, so I will start with, I call this seismic input parameters. Parameters related to earthquake ground motion that we use in seismic design. So that is the topic in this segment of the presentation. So what you see on the screen is the design spectrum of ASCE 705. Design spectrum means we have the seismic design force, let us say the base shear, given on the y-axis as a function of the period of the structure T. The period in turn is the period. If I point here, only the eyes can see, you cannot, and I cannot point backwards, so I will not try to point at anything. The period T is a function of the basic properties of the mass and the stiffness of the structure. Okay? So the seismic design force is given as a function of the basic properties of the structure. That's what a design spectrum does. Having said that, we have designed base shear on the y-axis. If you see the picture that I have on the screen, you will see spectral acceleration, S sub A, is on the y-axis. That is because it is directly related to basic shear. You take the spectral acceleration, multiply it by the mass of the structure, weight divided by G, you get the base shear. So it does give us the seismic design force as a function of the period of the structure. The spectrum in ASCE 7 has a flat top portion which is defined by this S sub ds. Let us say short period design spectral acceleration. Then it has a descending branch that varies with 1 over t, the reciprocal of the period. That part is defined by S sub d1, which is ordinate to the design spectrum at a period of 1.0 seconds. Okay? S sub ds defines the whole flat top, but it is defined specifically as the ordinate of the response spectrum at a period of 0.2 seconds. The two parameters, S sub ds and S sub d1, define the entire spectrum. Only additional thing you need is this T sub L, long period transition period. It is called in ASCE 7, where we go from the 1 over 2 branch to the third branch of the spectrum, which varies with 1 over t squared. Those of you into structural dynamics, for you, this is the constant acceleration part of the spectrum, this is the constant velocity part of the spectrum, this is the constant displacement part of the spectrum. Those things are unimportant. What is important is a short period structure, which are short stiff buildings, let us say, would be governed in its design by this flat top part of the spectrum. Taller buildings will be defined by this branch of the spectrum, the 1 over t part, and this third part seldom comes into play. You have to be designing a very tall building or a very long bridge to get into the third branch of the spectrum. This ramp building up to the flat top is really not a part of the spectrum. It is a device that gets very short period structures. Do not, all of it cannot respond immediately to earthquake excitation. So this provides a transition from 0 period to, we take this as 20% of the period at which we go from this branch to that branch. So this is a device that we use for very short period structures only when we do dynamic analysis, and normally we don't, which will be clear fairly soon. The two important parameters that we need, S sub ds, S sub d1, are not given anywhere directly in ASCE 7 or the IBC. What we are given are two parameters directly related to S sub ds and S sub d1. S sub s related to S sub ds and S sub 1 related to S sub d1. S sub s is the spectral acceleration at a period of 0.2 seconds, corresponding to not the design earthquake but something called the maximum considered earthquake, and for site class B, which is kind of soft rock. Okay? So everything I said is important. S sub s is ordinate to the design spectrum that we saw at a period of 0.2 seconds. This will define the flat top part of the spectrum. For or corresponding to the maximum considered earthquake for site class B. S sub 1 likewise is ordinate to the design spectrum at a period of 1.0 second, much longer than the 0.2. Also corresponding to the maximum considered earthquake, also for site class B, soft rock. Okay. US Geological Survey uses site class B as the benchmark site class. Now those values, S sub S and S sub 1, are given in maps in ASCE 7, but those paper maps are pretty useless because the scale isn't good enough for you to interpolate properly. We have to go to the US Geological Survey website to look up S sub S and S sub 1 for a particular site. That can be done by the postal address or by the latitude and the longitude of the site. So that's typically how it is used. The site class B that I talked about is one of 6 site classes that are defined in ASCE 7. Okay, so A is hard rock, which is in older parts of the world. In India, definitely there is the hard rock. Anyway, B is softer rock. C, D, E are progressively softer material. F is material so poor that to be able to design anything on it, you need a site-specific spectrum. The spectrum printed in ASCE 7 that I showed you is not going to do. Okay. Now in B and BC, the A, B, C, D, E are called SASB, SCSD, and SE. Site class F has been split into 2 site classes, S sub 1 and S sub 2. Okay. But the definitions are exactly the same. The distinction among the site classes is based on properties, measured properties of the soil at the site over the top 100 feet of the site. So you have to measure the properties of the soils over the top 100 feet. This and there are 3 properties that you can measure that I wouldn't go into. This particular slide tells you that if you are unable to measure properties, then the default site class is D. D as in David, unless the building department has figured out that softer E or F soil may exist at the site that you are building on. So D is the default site class, which is kind of important. Based on measurements, you can do better than D. Now, so the starting point in seismic design would be you look up S sub S and S sub 1 for your particular site. The second thing is you have to figure out the site class at the site of the structure, A, B, C, D, whatever. Once we have both, we will go to a table in ASCE 7 to find a short period site coefficient F sub A and a long period site coefficient F sub P. F sub A is a function of the site class and the short period mapped quantity S sub S. This is mapped ground motion parameter as opposed to design value, which will be S sub DS. In B and BC, in Appendix C to Part 6 that I was talking about, we have these values given, and then I will come to that. Let's forget about that detail. So F sub P, the long period site coefficient, is a function of the site class and the value of S sub 1, the long period parameter at the site. Okay. Now you should note, this is quite important, that the site coefficient is higher at the low seismicity end and lower at the high seismicity end. If the subsurface rock motion at the site is weak, as it will be in a low seismicity area, then it can be magnified 4 or 5 times by overlying soft soils, and that has happened. If the subsurface rock motion is strong, which would be the case in a high seismic area, then the magnification due to soft soil isn't that much. And that's kind of an equalizer. The motion that your structure feels, the motion on the surface, it is not all that terribly different. Like at rock level, there would be a big difference, but at the ground level, there wouldn't be so much difference because weak ground motion would be magnified more, bringing it closer to strong ground motion, which is magnified less. So I am not sure I was able to say it the best way, but it is important to remember that weaker ground motion is amplified more by softer soils than stronger ground motion. Once we have F sub A and F sub B, we modify the mapped short period ground motion parameter S sub S by the short period side coefficient F sub A, obtaining S sub MS, soil modified short period ground motion parameter, which still corresponds to the maximum considered earthquake. That hasn't changed. Okay. And we modify the long period map quantity S sub 1 by the long period side coefficient F sub B, obtaining S sub M1, the soil modified long period ground motion parameter that still corresponds to the maximum considered earthquake. The only difference between S sub 1 and S sub M1 is that S sub 1 is for site class B, S sub M1 is for your particular site class. Okay. Then for design, we use 2/3 of those maximum considered earthquake values. 2/3 of S sub MS is S sub DS, the design short period ground motion parameter that would define the flat top of the design spectrum, and 2/3 of S sub M1 is S sub D1, the design long period ground motion parameter, which will define the descending branch of the design spectrum. Okay? So now we have the design ground motion parameters. Now in the old days, before the IBC, this Uniform Building Code has been used worldwide, and the 97 edition was the last. Back in those days, we used to design to provide life safety in the 500-year return period earthquake, in an earthquake that is likely to occur once in 500 years. We have gone to avoiding to a different performance criterion, and I mentioned this in order to explain the 2/3 that I just talked about. Why is the design quantity 2/3 of the maximum considered earthquake quantity? Why couldn't we directly define design earthquake ground motion parameters? 2/3 is the reciprocal of 1.5. 1 divided by 1.5. 1.5 has been found to be the lower bound margin of safety that structures designed by modern seismic codes have. Modern seismic codes, by common acknowledgement, date back to the 1973 edition of the Uniform Building Code. So what we are saying is that a structure designed by 1973 UBC or a subsequent code is highly unlikely to collapse on us until the design ground motion equals and exceeds 1.5 times the design ground motion, which corresponded to the 500-year return period. Okay? Now, we are designing today for 2/3 of the maximum considered earthquake, because if we design for 2/3 of the maximum considered earthquake, the built-in margin of safety of 1.5 would ensure that we would at least barely avoid collapse in the maximum considered earthquake. Are you with me? So a margin of safety of 1.5 is built in, which means if we design for 2/3 of the maximum considered earthquake, we will be avoiding collapse in the maximum considered earthquake. And that is the performance criterion of IBC seismic design. We are now designing to prevent collapse in the maximum considered earthquake as opposed to providing life safety in the 500-year return period earthquake. Now it can be shown that if we do what we are doing now, the previous performance criterion is met, we will automatically be providing life safety in the 500-year return period earthquake. That has not been forgotten. We are explicitly doing something else. Now the maximum considered earthquake, I have not defined yet, you must have noticed. So in the source document from which all of this comes, and I wouldn't go into details of that, the definition is maximum level of earthquake ground shaking that is considered reasonable to design buildings to resist. That word reasonable makes this definition pretty much totally useless. You know, you cannot define something in terms of what is reasonable. That's your judgment. You know, that's nothing objective. So this is kind of a declaration of principle rather than definition. The actual definition that was built around that declaration of principle became, at least for the United States, a two-part definition. It became a two-part definition for a very good reason. And I'm going into this only because I want to explain why in Bangladesh it is not a two-part definition. In the US, or actually the coast of California is the only part of the Earth's crust where seismologists pretty much know the seismic sources, the faults and things that can generate strong earthquakes. And by and large, they also know the capabilities of the seismic sources, what they can generate by way of strong ground motion. And since they know, the decision was made that the maximum considered earthquake of coastal California would be the largest earthquake that can be delivered by the known seismic sources. Okay? Now, elsewhere, outside of coastal California, where seismologists do not have anywhere near the same handle on the seismic sources or their capabilities, they agreed, knowledgeable seismologists agreed, that the event that comes the closest to the maximum considered earthquake of coastal California is an earthquake having 2% probability of exceedance in 50 years, which corresponds to a return period of 2,500 years or so, 2475 to be more exact. Okay? So this 2,500-year return period earthquake is the maximum considered earthquake pretty much everywhere outside of coastal California. In BNBC, this is the definition of maximum considered earthquake. You do not have major seismic sources that can cause an earthquake. How should I? This necessity to cap the reason for what is done for coastal California is that the known seismic sources are too weak to deliver 2,500-year ground motion. So we go with the largest that can be delivered. Now there is no reason to how should I say, the sources that can contribute to seismicity here in Bangladesh do not warrant this kind of a deterministic cap. So the definition of the maximum considered earthquake is simply that it is 2,500-year return period earthquake, and we are designing for 2/3 of that earthquake. So I am back to the spectrum that I started with. The only difference is now we know that it corresponds to the design earthquake, which is 2/3 of the maximum considered earthquake. Also, I did not, so S sub S is mapped, S sub 1 is mapped, S sub S gives us S sub ds, S sub 1 gives us S sub d1, but to define the entire spectrum we need another quantity, this T sub L. And that is mapped for the United States, and that map is in ASCE 7. Okay. Now let us go to BNBC 2017 and Bangladesh. Now the writers of this code have modified ASCE 705 in some ways. Dr. Rakib was one of them. He definitely is more knowledgeable about these things than I am, and I told him if I say something not right, he will correct me, and I was totally serious. So, because I definitely don't know as much. Anyway, Bangladesh in BNBC 2017, and this was the case in 2006 also, has been divided into seismic zones 1, 2, 3, 4. Okay? All of you know that now in Appendix C, we have the S sub S and S sub 1 values given by the seismic zone. So here in Dhaka, you are in seismic zone 2. So S sub S value is 0.5 and S sub 1 is 0.2. We don't have to go to a map or US Geological Survey or anything like that. Right? So it is significantly easier. Then the F sub A and F sub B, by which we have to modify S sub S and S sub 1, are given in tables, and I found it kind of interesting that there are columns for the 4 zones, but the values never change. And anyhow, so that's something I did want to point out, that we have only one set of values. The F sub D table is similar. We have a table for F sub D that gives us F sub D by the seismic zone, and obviously the site class of the site. Okay, so the S sub S, S sub 1 values for the different zones, I have to stand somewhere else here, are given in what happened? Okay. So S sub S and S sub 1 for the different zones are given in Appendix C. F sub A and F sub B for the different zones and different site classes are given in Appendix C. And it's kind of nice that they have also calculated the S sub DS and S sub D1 values for you when they're given in tables. So you don't have to do as much work as we have to do back in the US to get to S sub DS and S sub D1. Okay? Those are tabulated for you by the seismic zone. So that was S sub DS, and this is S sub D1. Now the spectrum in BNBC is the same as the ASCE 7 spectrum, except this T sub 0 is called T sub B. The T sub S of ASCE 7 is called T sub C, and the T sub L is called T sub D. Okay? So T sub B, T sub C, T sub D, I don't know what happened to T sub A because it is notation for period when you didn't use it. Yeah, I don't know. Anyway, so T sub B, T sub C, T sub D. Those values are given to you for the different site classes. And you see the values if you are designing by ASCE 7, it is not that simple. Nobody gives you the values. The T sub S is S sub D1 over S sub DS. The T sub 0 is 20% of T sub S. We have to figure both out. And T sub L, which is T sub D here, is given on a map. If you look at the US map, the value of T sub S varies between 4 and 16 seconds. In BMBC, the value is fixed at 2.0 seconds for the entire country. So this is whole lot shorter than what we use in the US, and I don't again know the background. There must be some background to it, but for design purposes, the main thing is that the spectrum is defined for you. The T sub B is given, the T sub C is given, T sub D is given. So design by Appendix C should be pretty simple, it seems to me. Once you have your spectrum, we will go to other places in a second. I did want to mention to you that in ASCE 710, the edition subsequent to the one we are talking about, very significant changes happened in the ground motion that is mapped. We went from maximum considered earthquake to risk targeted maximum considered earthquake ground motion. It is now MCE sub R. Okay. Now the difference, and I'll try to explain very briefly because I don't want to spend time on this. This is maybe in the future, maybe not. So to US Geological Survey, first of all, the ASCE 7 maps are based on maps issued by US Geological Survey. The maps in ASCE 705 are based on US Geological Survey maps dated 2002. Then there are maps dated 2008 and then 2016. Okay. So the US Geological Survey maps change, and that resulting changes in ASCE 7. 2% probability of exceedance in 50 years. 2% probability that the mapped ground motion would be exceeded in 50 years. The reason for switching to MC sub R was people decided that uniform probability of the mapped ground motion being exceeded should not be an end in itself. We are engaged in structural design. What we should have uniform across the country is the risk of structural collapse if the mapped ground motion is exceeded. There is a subtle but very, very significant difference. So instead of having a uniform probability of the mapped ground motion being exceeded, what we should have uniform is the probability or the risk of structural collapse if the mapped ground motion is exceeded. So we have gone from 2% probability of exceedance in 50 years of the ground motion itself to 1% risk of structural collapse if the mapped ground motion is exceeded. So this 1% risk of collapse in 50 years is uniform across the country, and that gives us the risk targeted part of the name. Okay, and it is MC sub R because of that. This is a conceptually difficult, and there are problems with it, and I would say right here and now that when you update BMBC beyond the 2017 edition, this is something I think you should reject. The risk targeted ground motion is not necessary at all, and the values are not that terribly different. Anyway, but this is what you see in maps in ASCE 7. The other thing that happened, this is in magnitude a bigger difference. Up until this change took place, the change that I'm going to talk about, I did not even know that the S sub S and S sub 1 values we were getting on maps were so-called geo-mean ground motion values. The square root of the product of ground motions recorded in two orthogonal directions. That's what US Geological Survey was mapping. Square root of the product of ground motions recorded in two orthogonal directions. From that, we have now gone to ground motion in the direction that can cause, that does cause maximum structural response. This is called maximum direction ground motion. So ground motion in a direction that causes maximum structural response. This maximum direction ground motion was obtained by multiplying the S sub S value of ASCE 705 by a scalar multiplier of 1.1, just 10% increase, and the the maximum direction value of S sub 1 was obtained by multiplying the S sub 1 of ASCE 705 by 1.3. And there is basis to the multipliers, but anyway, you can see that I'm not enthusiastic about this either. So the switch from ASCE 705 to ASCE 710 ground motion is something that I think when the time comes, you should simply reject it. It is not necessary. Anyway, if we get S sub S and S sub 1 of the MC sub R values of S sub S, S sub 1 also from the US Geological Survey website. That website used to give us at one point S sub S and S sub 1 values for locations outside of the United States. That has been discontinued. The only place where sitting in the US you can get S sub S and S sub 1 for locations outside of the US are in this document published by, it is called the Unified Facilities Criteria, that is published by the US military. And I bring this up because these UFCs, as they're called, Unified Facilities Criteria documents, are available free of charge on the internet, and many of them are just excellent sources. If you want to do seismic design of dams, the UFC is probably the best document that is available. So this is a source that is easily accessible, and I think you should use it. So there is a structural UFC, as it is called. The number is given. We actually update that for the military on a regular basis, and in that we have tabulated values of S sub S and S sub 1 for any location where US military has some kind of an installation, and for some other locations. But I will tell you that those values are some places quite good, some places not so good, and that is acknowledged in the document itself. And the advice is that where they are not so good, you do site-specific, you find site-specific ground motion. Anyway, so let me, I don't, you left the cricket match, I don't want you to keep out of bed or anything like that. So how long is reasonable?
Doesn't matter, so please carry on.
To cause any kind of, no, I know it is important, but at the same time I cannot finish in 20 minutes. Yeah. Oh, okay, thanks. Thank you. So let's go to the next important issue, and I titled it Seismic Zone versus Seismic Design Category. In the old days of the UBC, I go back, we had seismic zones, 0 through 4, 0, 1, 2A, 2B, 3, and 4. And the zone told us we have, for definitely concrete, also steel, we have 3 levels of detailing. Seismic design, the design for the seismic forces that I was talking about is definitely important, but that goes hand in hand with detailing, as we call it, and it is called detailing in BMDC also. In reinforced concrete, it means how you arrange the reinforcement in a member, how much transverse reinforcement, how much confinement reinforcement you have in addition to the longitudinal reinforcement, the spacing, the size, and all of that. So we have 3 levels of detail: ordinary, intermediate, and special. The zone determined the level of detailing we had to do for a structure. In zones 0 and 1, we were allowed ordinary detailing. In zone 2, we had to do intermediate detailing as a minimum. And in zones 3 and 4, the minimum detailing was special detailing. Okay. The detailing was, important as it is, was not the only thing that was determined by the zone. We have height limits on structural systems, particularly in the high seismic. So we have height limits on structural systems. Those depend on the seismic zone in which a structure is located. Most height limits apply to zones 3 and 4 only. Lower seismic zones, we did not have height limits. Also, zone determined whether we could design on the basis of equivalent static analysis or whether we had to go to dynamic analysis as the basis of design. IBC does not have seismic zones, simply does not have seismic zones. So what determines, what makes these important decisions for us? How do we know whether we have to do ordinary, intermediate, or special detailing? So the role that used to be played by the seismic zone in the UBC is now played in the IBC by the seismic design category, okay? SDC for short. Seismic design category is a function of 3 things. It definitely is a function of the seismic hazard at the site, which is what the seismic zone was all about. But it is also a function of the occupancy of the structure, whether it's an office building or a hospital makes a difference. And very, very importantly, it is a function of the soils at the site. Okay? So the soils at the site now determine what kind of detailing you are going to do for your structure. This was a huge departure in the IBC from the UBC days. This was a major change in seismic design practice. Okay. So we determine the seismic design category of a structure. First, from this table in ASCE 7, where it is a function of the risk category. In BNBC, it is still called occupancy category, which was the name up to ASCE 702. We switched to risk category in ASCE 705. It is the same thing. There is really no difference. Okay? But whenever you see risk category on my slides, just think occupancy category. So the seismic design category in this table is a function of the occupancy category and the short period design ground motion parameter S sub ds. So this combines seismic hazard and the soils at the site. And you see that the table gives us A, B, C, or D. We then redetermine the seismic design category of the same structure from the second table, where it is a function of the risk category of the structure and the long period design quantity S sub D1. And we take the worst of the two. If based on S sub ds, the seismic design category turns out to be C, and based on the S sub D1, it turns out to be D, the seismic design category is D, not C, the worst of the two. Okay? So the two tables give us A, B, C, and D. Then there is language in ASCE 7 that tells us if our structure is located where the long period mapped quantity is larger than or equal to 75% of G. This can happen only in the vicinity of known faults that can generate large earthquakes. So in those near fault locations, an essential facility, a hospital, a police station, or a fire station would be design category F. Everything else would be design category E. Now in Bangladesh, you do not have this high seismicity situation. S sub 1 going beyond 0.75, so you do not have E or F. You also do not have the low seismicity situation that gives you design category A. Okay? The lowest ground motion, the lowest value of S sub D1 will be larger than 0.67. So you have only design categories B, C, and D. And those are given in BMBC in this table. The table looks different in the code, but it is the same table. So depending upon the occupancy category it is called, and the seismic zone and the soils at the site, the seismic design category of the structure is given. Occupancy categories 1, 2, and 3, it is given in this part of the table. Occupancy category 4, it is given in this part of the table. And as I said, it is B, C, or D. You don't have any A, you don't have any E or F. So, design category determination by BMBC will be by this table, one table. You don't have to worry about the two tables and taking the worst of the two and so forth. This I threw in just to tell you essentially that in your case where you have B, C, and D, B would be what we always regarded as low seismicity, where ordinary detailing is allowed. C is moderate seismicity, comparable to zone 2 of the UBC, where intermediate detailing is allowed. D is high seismicity, comparable to zones 3 and 4 of the UBC, where we must do special detailing. Building configuration, very important. In BMBC, you have something we do not have in ASCE 7. There is very good guidance given. Your structure should be simple. Your structure should not have a lot of torsion. Those are essentially mostly not up to us. The owner and the architect tell the structural engineer what to design, and if you are in Dubai, the structure will look like totally against all common sense. It will increase in plan area as you go up, and you have to design what you get. But to the extent that it is up to you, those principles are just excellent advice. Yeah. Now, building configuration is very, very important in that context. Structurally irregular buildings attract incomparably more damage to themselves in an earthquake than regular buildings do. And this you should remember for all time to come. So to deal with that, back in 1988 Uniform Building Code, a long time ago, the code, somebody has to tell me when the 20 minutes was. I have got 10 more minutes. Okay. You will tell me when to break, okay? So in 1988 UBC, we came up with a table of, those days it was called land irregularities, now we call them horizontal irregularities. That table with a couple of modifications still continues in the current edition of ASCE 7. And there was a second table of vertical irregularities. Now in ASCE 7, all the definitions, let me show you the list first of all. So the horizontal irregularities are types 1A, 1B, both are torsional irregularity. 1B is called extreme torsional. 2 is re-entrant corners. I think most of you understand what that is. 3 is diaphragm discontinuity. If you have a big opening in your slab, you may get there. Out of plane offset of the seismic force resisting system is 4. 5 is non-parallel seismic force resisting system. You have exactly the same in BMBC, except that 1A and 1B are one category, just one. 1, 2, 3, 4, and vertical, we have stiffness irregularity, very, very important, or soft story, where one story is much more flexible than the stories right above and below. That causes huge problems. I mean, it's incredible how much damage is caused by just that irregularity. Okay, so we have soft story and extreme soft story in BMBC. It is just soft story. So vertical type 1. Then weight or mass irregularity. In ASCE 722, it will go away. It has been found now that it doesn't make any difference. After all this time, that was figured out, but you have that. Vertical geometric irregularity, that would be like that building. In-plane discontinuity in vertical seismic force resisting elements. And then weak story. Soft story means the stiffness is very different from one to the next. Weak story means the strength is very different from one to the next. Weak story is in some ways worse than soft story. Quite often soft story and weak story go together. If something is more flexible, it is also weaker. Anyway, so the definition of each, this is what I want to convey to you. In ASCE 7, the definition of each one of these irregularities has a threshold. Up to that threshold, it is not considered irregular at all. Beyond the threshold, you consider the structure to have irregularity type whatever. And I chose not to go into detail of this because even the long presentation I prepared doesn't work in that. Now, in addition to the definition involving a threshold, the way irregularity is handled is if you have type 1A irregularity, there is a table that will tell you sections such and such, and there may be a list of 6 different sections and subsections of ASCE 7 that become applicable to your case. So in the design of your structure, having torsional irregularity type 1A, you have to comply with subsections this, that, and that. Okay. So this is how it is handled. Almost nothing is outlawed except the weak story irregularity in near fault locations. Everything is permitted, but you have to do sophisticated analysis most of the time. Sometimes there is some penalty and so forth. In BMDC, the treatment is not as elaborate in ASCE 7, but it has the same kind of essence to itself. Okay, next is, and I will do that and then we will take the break. So, methods of analysis. In ASCE 7, there is a simplified analysis that was, I think, rightly and justifiably left out of BMDC. It's pretty useless and I wouldn't go into that. Then, equivalent lateral force procedure, which we use most of the time, I would say. Then modal response spectrum analysis, which is given in detail in BMBC, not given in such detail in ASCE 7, but it's the same procedure. Then time history analysis, we also call it response history analysis, where you subject the structure you are designing to actual recorded earthquake ground motion. And you analyze the response on the computer in very short time increments. If you assume that your structure remains elastic throughout its response to the input earthquake ground motion, then it is elastic response history analysis, which in my opinion does not give you any more information than you can get from modal response spectrum analysis. So I personally am not a fan of elastic response history analysis, but in elastic response history analysis, so we should quit. Yeah, okay.
The other mic is running out of battery. I don't know why. I'll try this. is much more difficult. This is for show business people, not for me. Anyway, I'll try. So we talked about the different methods of analysis recognized by ASCE 7, except that I didn't go to the last slide. Nonlinear response history analysis is where we recognize in the analysis that in the way we design our structures, in a design level earthquake, definitely in the maximum considered earthquake, the structure will go inelastic in various locations of various structural members. In order to recognize that in the analysis, we have to have models for the behavior of these localized regions. Anyway, nonlinear response history analysis today is the most sophisticated analysis we have at our disposal. It tells us probably the most about seismic response. And today, the design of most important buildings is based on nonlinear time history analysis. The trend is more and more towards nonlinear time history analysis. Now, this slide, I don't know how. So this slide is about permitted. This slide is about permitted analytical procedures. The main thing we are discussing here is where we are forced by our code to do dynamic analysis as the basis of design. When equivalent static analysis will simply not be permitted. So this chart so this flow chart tells us if the design category of our structure is coming in and out. If the design category of our structure is B or C, okay. If the design category are B or C, no, it didn't improve. Then dynamic analysis will never be required by ASCE 7. If the design category is D, E, or F, and we have a risk category 1 or 2 structure, so that excludes assembly buildings and essential facilities, less than or equal to 2 stories tall, then also dynamic analysis will not be required. This category 1 and 2 up to 2 stories, no matter how irregular it is, dynamic analysis will never be required. This box is not relevant for Bangladesh. This light frame construction is not something you have, I don't think. So let me not go there. If you have a design category D, E, or F structure, that is not a risk category 1 or 2 structure up to 2 stories, then if the structure is up to 160 feet in height, up to 160 feet, then we look at whether the structure has certain types of irregularities. I will call them simply for our purposes now, quote unquote, bad irregularities. Torsional irregularity will be a bad irregularity. So if a structure up to 160 feet tall has one of the bad irregularities listed in this box, you have to do dynamic analysis as the basis of design. If it does not have any of those irregularities, then equivalent static analysis shall be permitted. So irregularities that are not listed in that box do not count as irregularities. They are treated as regular structures.
Now, if a structure is taller than 160 feet in height, then equivalent lateral force procedure will be permitted only if the structure has no irregularities, good or bad. And in addition, the period of the structure is less than 3.5 times the transition period that I talked about, S sub d1 over S sub ds. S sub d1 over S sub ds is typically about half a second, 0.5 second, thereabouts. 3.5 times half a second would be 1.75 seconds. That would be the period of a 17-18 story frame building. So if you have a frame building up to 17 stories tall, you can do equivalent static procedure. If it is more than 17 stories, you have to do dynamic analysis. Okay? So your structure has to be totally without any irregularities, and in addition, the period has to be less than 3.5 times the transition period. If you do not satisfy both of those requirements, you have to do dynamic analysis. Okay? So this is a summary of ASCE 7 requirements concerning permitted analytical procedures. The slide is in your handout, and I think you will find it useful. Okay, let me now go into this equivalent lateral force procedure, which, as I said, is the procedure we use more often than not for seismic design purposes. So we start with the design base shear V, which is equal to a coefficient C sub S times the seismic weight of the structure. This W is not just the dead load of the structure. That is very important to understand. Seismic weight basically is the weight that is expected to be shaken in the design earthquake. So in a storage facility, we include a part of the design live load in seismic weight, because a warehouse is unlikely to be totally empty when the design earthquake hits. So that's the idea. Okay? W is specifically defined in ASCE 7, also in BNBC, and I'll show you both definitions. The C sub S is given by essentially the design spectrum that I showed you modified, and then I'll come to that in a second. So let us deal with the seismic weight first. So W is total dead load and applicable portions of other loads. In the US, we include 25% of storage live load, storage facilities. Minimum of 10 pounds per square foot, I put the equivalent, I hope I did the conversion right, half a kilonewton per square meter for partition loads. When the partitions are movable, we have to include that 10 pounds per square foot. Weight of permanent equipment, the snow load is pretty complicated, but you don't have that, so I wouldn't go there. And weight of landscaping and roof gardens. More and more people have gardens on their roofs, swimming pools on their roofs, and so forth, and you have to include those weights. Now in BNBC, it is quite different actually. Seismic weight is the total dead load of a building, including partition walls and applicable portions of other imposed loads listed below. And what is listed below is for live load up to and including 3 kilonewton per square meters. That is, what is it? 1.5 is 30, so this is 60 pounds per square foot. A minimum of 25% of the live load shall be applicable, 25% up to 60 pounds per square foot. Beyond that, it is 50% of the live load that is to be included in the seismic weight. This is significantly different than ASCE 7, as you can see. Then, total weight of permanent heavy equipment, retained liquid, any imposed load sustained in nature shall be included. This heavy equipment, I do not know what the heavy is supposed to mean when it becomes heavy. Anyway, so this is exact language out of BNBC. In applying the code, those things become a little bit of a problem when you throw in words like that. And Anyway, then it goes on to say where the probable imposed loads at the time of earthquake are more correctly addressed, the designer may go for higher percentage of likelihood. The details are not terribly important. I just wanted to point out that this part is different in BNBC than in ASCE 7. Now, when we do equivalent lateral force procedure, we modify this elastic response spectrum or elastic design spectrum that we have seen so far in 4 different ways. We do not use this spectrum directly as it is in equivalent static procedure. The 4 modifications are, number 1, the ramp building up to the flat top. This ramp is eliminated. The flat top is extended all the way back to 0 period. Okay? Modifications number 2 and number 3, very importantly, we lower the elastic design spectrum by the response modification factor R. At the same time, we raise it by the importance factor I. Okay? So we lower the design spectrum, the elastic spectrum, by the response modification factor R, at the same time raise it by the importance factor I. The R is something very important that I will explain in just a little bit. I simply increases the design force for more important structures like hospitals and schools and so forth. Okay. Now, you should notice that it is written as the elastic S sub ds times W divided by R over I. Instead of saying multiplied by R divided by I, it is dividing by R over I, which is arithmetically the same. But we write it this way because the idea is that you how do I want to, so the R accounts for, let me go into it a little bit. R accounts for the inelastic deformability, that's how I will describe it, of the seismic force resisting system that we are utilizing in our design. Inelastic deformability means the range of inelastic deformations that can be, over which gravity loads can still be sustained. And let me talk about elastic inelastic first. Elastic does not necessarily mean force proportional to displacement. Elastic response means all the deformations that take place are recovered. The earthquake passes, you get your structure back intact and very importantly located where it used to be before the earthquake, not some distance away. Okay. Now that means there is no damage associated with elastic response. Okay. Now, once structural response ceases to be elastic, we are dealing with inelastic deformations that have damage associated with them. Once you go into the inelastic range, you will not get your structure back intact anymore. You will have to repair it following the earthquake. Okay. Now these inelastic deformations that we are going to allow in our structure have to be within the inelastic deformability of the structure for it not to collapse on us. So inelastic deformability again is the range of inelastic deformations where the factor gravity load can still be sustained. The longer the range of inelastic deformations over which gravity can be sustained, the higher the inelastic deformability, the lower the need for strength. And in those cases, we use a high R value in design. Okay. The lower the inelastic deformability, the shorter the range of inelastic displacements over which gravity can be sustained, the lower the inelastic deformability, the higher the need for strength. Now we need to design for lower R values. Okay? So R accounts for inelastic deformability of the structural system that we are utilizing to resist earthquake forces. Now when we show this R over I, it means that for, let us say, hospitals, I is equal to 1.5. For a specially detailed moment frame, R value is 8. When we are designing a hospital building utilizing special moment frame, instead of utilizing an R value of 8, we are utilizing 8 divided by 1.5, which should be 5.5 or something. That means we are allowing lower inelastic displacements in the design earthquake, which should mean less damage to non-structural elements, equipment, etc. that are mounted on the floors. Okay, so that is the idea. In a hospital, we want the equipment to be functioning during and following an earthquake, and that is not ensured, but that's what we are trying to accomplish by utilizing a lower R value for higher occupancy category structures. Okay, so R over I. The final modification we make, modification number 4, I said 4 modifications, is that at the long period end, where this 1 over T or 1 over T square relationship will give us very low design base shear. We do not want to design for very low base shear, so we put a floor on it. We put a lower bound value on the design base shear that we are going to design for. In the US, we have 2 lower bounds, one applicable in all seismic design categories, the other one where the mapped long period quantity S sub 1 is larger than or equal to 60% of G. This is the equivalent of all seismic zone 4 of the UBC. This you do not have in Bangladesh. So the second minimum does not even appear in BMDC 17. This 0.044 S sub ds IW is used exactly as you see it on the screen. Now in the US, parts of the US have very low seismicity. If S sub ds is very low, it will give us very low design base shears again. So we put a floor. This number cannot be any less than 1% of the weight of the structure. That again is unnecessary here because you don't have very low seismicity. So that floor on BMDC just tells you 0.44 S sub ds I times W. It does not say that it cannot be any lower than 1% of weight because that's unnecessary. Okay? Now, unless you have a very short, stiff building governed by this part of the spectrum, in order to find the design base shear, you will need the period of the structure T. I told you at the very beginning, T is a function of the mass and the stiffness of the structure. Until we have designed our building, we do not know the mass, we do not know the stiffness. How are we going to determine period? So this is the classic chicken and egg situation. We cannot do seismic design without a period. We cannot find period without having done seismic design. So our codes give us approximate period formulas. The intent of which is to get us started. We start with approximate period, and then having gone through part of the seismic design, if we choose to refine our period estimate, we are allowed to do so. We are allowed to calculate period by any rational procedure that is in compliance with the principles of mechanics. Now, there is a catch. A rational period determination depends on your stiffness assumption, particularly if it is a concrete or a masonry building. By taking cracked rather than close stiffness, and by taking crack stiffness very low, you will be in a position to calculate a period as long as you want it to be, which then will translate into a design base shear as low as you would like to design for. That is not the idea behind the privilege of rational period computation. It is not supposed to be a license to lower your design base shear as much as you would like. So we have a control on rationally computed period. You can calculate anything you want, but you cannot use anything higher than a multiplier C sub u times the approximate period. Okay? This multiplier, okay, before I come to the multiplier, okay, let me talk about the approximate period. So today in ASCE 7, and this part is exactly the same in BNBC, the approximate period is given by a coefficient times height raised to the power something. The coefficient, so for steel moment frames, the coefficient, if you have the height in feet, that is the coefficient, you have the it will be close to that, I think. Yeah. I'll try my best. Yeah. So if the height is in feet, that is the coefficient. If the height is in meter, that is the coefficient. So 0.028 height raised to the power 0.8 for steel moment frames. Concrete moment frame 0.16 height raised to the power 0.9. For eccentrically braced steel frames or buckling restraint brace frames, I don't know if you have them here, that is pretty popular now in the US. Eccentrically braced is really not used anymore, but buckling restraint is quite popular. So 0.3 height raised to the power 3/4. Everything else, concrete building with shear walls, height, the 0.2 height raised to the power 3/4. So that's what we use day in and day out. Okay? Frame buildings of concrete cannot be built very tall, efficiently and economically. So beyond a certain height, and that height isn't all that terribly, like I would say beyond 12, 13, 14 stories, you probably better have shear walls in your building. You can do without that, but your design will be inefficient. Anyway, so the rationally computed period, if you choose to do rational period computation, cannot exceed, as I said, a multiplier times the approximate period. In the US, the multiplier is a function of S sub D1, the long period design ground motion parameter. In BNBC, you have a fixed value of 1.4. So rationally computed period by BNBC cannot be any higher than 140% of the approximate period. Simple. Okay? Now, that limit that I just talked about is mandatory for force computations when you design. But if you are calculating deflection, that limit, upper bound limit on rational period need not apply. If you keep it in place, it's fine. If you don't want to keep it in place, so you calculated period of 2 seconds. And C sub u T sub A is 1.6 seconds. In deflection calculation, you can use 2 seconds. And that is allowed because if you are calculating a long period, that's because you have assumed very low stiffness. And if you have assumed very low stiffness, you'll be calculating very large deflections. And the code doesn't have any problem with it. If you want to shoot yourself in the foot, you know, that's totally fine. So the limit on rationally computed period need not apply in deflection computations. Okay. So this is, yeah. I was told to kind of complete it sooner rather than later, but this is extremely important. So I would like to spend a couple minutes on this. Okay. So what we are showing in this picture is the force displacement relationship of a particular structure subject, let us say, to the design earthquake of ASCE 7 or BNBC 17. One structure subject to the design earthquake of the code. Now, if the structure were to remain elastic in the design earthquake, in the process of going through the design earthquake, the force induced in the structure would have been V sub capital E, and the total displacement suffered by the structure would have been delta sub capital E. Okay? Now, if I turn around and say we are required to design this particular structure for elastic response to the design earthquake, the immediate conclusion would be that we must design it for a strength equal to V sub E at least. If we decide we cannot afford that high strength level, that all we can afford is a much lower strength level V, what would happen is when the earthquake-induced forces equal and then exceed the supplied strength level, the structure will start going inelastic. It will start cracking and yielding in places. So that would be the beginning of inelastic behavior. Okay, now the R factor that I talked about is the ratio between the strength level for which we are designing and the strength level that would have given us elastic response to the design earthquake. Okay? So that needs to be absolutely clear. Now I could complicate the picture, like when you design for an R of 8, it is really not 1/8 of the elastic force level that we are designing for. It is something closer to 1/4, but let us not go into those complications. R is essentially the reduction we take on the design force that would have been needed for elastic response to the design. Okay. There are two other parameters that we absolutely need to know about and worry about. So we take the design base shear V, distribute it along the height of the structure in the manner prescribed by ASCE 7 or BNBC, the same distribution. And I'll show it to you very soon. Once we do the distribution, we have lateral forces acting at the various floor levels. We carry out an elastic analysis of our structure under those distributed forces. That gives us elastic deflections at the various floor levels. The elastic deflection at floor level X is denoted by lowercase delta sub X sub E for elastically computed. That delta sub XE is much lower than the deflection floor level X will actually undergo if the design earthquake were to hit, because we made the structure so weak, we designed for a much lower strength level than would have been needed for elastic response to the design earthquake. So the deflection we actually expect at floor level X in the design earthquake is estimated by multiplying this elastically computed deflection by a factor C sub D, which is called the deflection amplification factor. Okay? So deflection amplification factor takes us from elastically computed deflection under the code prescribed seismic forces to estimated design earthquake deflections. Okay? If I'm unclear any place, please raise your hand and I'll try to clarify. Okay? There is a third parameter that you need to be absolutely aware of. And let me try to explain it this way. So the same analysis that gave us delta sub XC, elastic analysis of the structure under code prescribed seismic forces, will give us bending moment, shear forces, axial forces at various critical sections of area structural matrix. Let us say we calculate 200 foot-kips of negative bending moment at the support section of a beam from that analysis. If we want to figure out the very largest bending moment that can develop at that section under the design earthquake, our estimate of that would be the carried by omega sub 0, an overstrength factor, which is given along with the R values in ASCE 7 table 12.2-1, and the omega sub 0 is either 2, 2.5, or 3, depending upon the structural system that you are talking about. For a special moment frame, omega sub 0 is 3, which means if elastic analysis under code prescribed seismic forces gives us a negative bending moment of 200 foot gips at a beam section, the actual negative bending moment that can develop at that section is 600 foot gips. Okay? So R, omega sub 0, C sub D, those are the three seismic design parameters that we need. All three are given in that table that I told you about 12.2-1 and essentially reproduced in BNBC as far as I know without any change, but Dr. Rakib can tell you if they made any changes. So R, the highest value we have is for the specially detailed moment resisting frame system. It's not the lowest, but another benchmark value is R of 5 for a bearing wall system, and I will define them in just a second, that features being pushed concrete shear walls that are specially detailed. R of 5, R of 8 gives you an idea that we would design a shear wall structure for roughly twice the base shear, for which we would design a frame structure. Okay? Because a frame is more inelastically deformable, a shear wall structure is not so inelastically deformable. That's the point that I'm trying to make. It is roughly 1/2, 5 to 8. Okay, let's talk about the structural systems. 4 structural systems are recognized in ASCE 7 and BNBC. The upper left is moment resisting frame system, which means beam column frames or slab column frames, as the case may be, resist gravity as well as lateral loads. Frames carry gravity loads, the same frames carry lateral loads. There are no shear walls doing anything for us. The second system is called a bearing wall system. In the old days, we used to call it a box system. Okay? Bearing wall system now. We have bearing walls carrying all the gravity. Bearing wall is a wall that so you have a wall standing there, and you hang a bunch of photographs on the wall. Does it become a bearing wall? And the answer is no, because those photographs don't do anything to the wall. So there has to be again a threshold beyond which, if the gravity load exceeds a certain threshold, we call it a bearing wall, and that threshold is defined in the code. Shear wall, on the other hand, means a wall that resists in-plane lateral loads as opposed to out of plane. Okay? So in a bearing wall system, bearing walls carry gravity loads, and the same bearing walls acting as shear walls resist earthquake forces. Now this is a problem. You are depending on walls that carry gravity for you to resist earthquake forces, which means if something happens under an earthquake to these walls, you do not have gravity carrying capacity. And this is why the R value is among the lowest of the 4 systems that I'm going to talk about. Okay? Then there are shear wall frame systems in which we utilize shear walls as well as frames. Those can be designed in one of 2 ways, as a building frame system or a dual system. So a building frame system, and the name is very unfortunate, a building frame system is not a frame. In a building frame system, essentially complete frames carry substantially all the gravity. The 2 words I threw in, essentially and substantially, are both important, but I wouldn't go into it too much because of time limits. Essentially complete means doesn't have to be 100.00% complete. And substantially all the gravity means 100% of the gravity does not have to be carried by the frames. Yeah? Basically that's what it is. So the 100% of the gravity is carried by, not 100%, substantially all the gravity is resisted by essentially complete frames, and 100% of the seismic forces is resisted by shear walls. So gravity resistance and seismic resistance are totally separated. This is the building frame system. In this kind of a system, it is absolutely essential that you check and make sure that the gravity carrying frames will be able to sustain their gravity load carrying capacity as they ride together with the shear walls up to the design earthquake displacements. This is called the deformation compatibility requirement. If you have not made sure that the gravity will be sustained up until the design earthquake displacements, you are not preventing collapse of your structure. Okay. The final system is the dual system where we also utilize frames and shear walls, but now both the frames and the shear walls participate in resisting gravity as well as lateral loads. If you analyze a shear wall frame system on the computer the way you should, you will see that near the bottom of the building, 100% of the story shear goes to the shear walls, nearly 100%, with the frames carrying nothing. As you go up, the frames pick up more and more and the shear wall carry less and less. You have to design the frames and the shear walls on that basis. You have to design the frames for what they carry, you have to design the shear walls for what they carry. Okay? In addition, the frames must be designed to resist at least 1/4 of the design lateral forces independently of the shear walls. This is also very important because if you just design the frames based on what they carry, the frames towards the bottom of the structure will be very weak because they don't resist much. And we don't want weak frames near the bottom of our structure because if something should happen to the shear walls, the frames wouldn't be carrying gravity anymore. So this is why this so-called backup frame requirement. The frames must be designed to resist at least 1/4 of the design lateral forces independently of the shear walls. Okay? Now, there are other systems that we built. I don't want to say all the time, but they are built fairly often. Those are undefined structural systems that must be designed by comparison with one of the defined systems. You have to figure out R omega sub 0 C sub D by comparison with one of the defined systems. Okay, the ASCE 7 table 12.2-1, I don't want to spend time on it. I value that we discussed. I is one for risk category or occupancy category 1 or 2. Occupancy category 1 is miscellaneous occupancy where no life safety is at stake. Occupancy category 3 is where a lot of people congregate in one space at one time. Essential facility, risk category 4. Risk category 4 is essential facility or hazardous facility. If you store chemicals in a building, that would be risk category 4. Risk category 4, we use an R of 1, an I of 1.5. The assembly buildings are I of 1.25. The miscellaneous occupancy 1.0. But the important thing is any building that is not risk category 1, 3 or 4 is 2. So most things we design, all residential buildings, office buildings, those are risk category 2 and they're designed for an I of 1. Okay? The distribution of the story shear, not story shear, the base shear along the height of the structure. So if the period of our structure is up to half a second, we do a linear distribution of the design base shear, triangular distribution, going from 0 at the base to a maximum at the top. If the period is larger than or equal to 2.5 seconds, we do a parabolic distribution. In this expression, K of 1 will give you a linear distribution, K of 2 will give you a parabolic distribution. If the period is between half a second and 2.5 seconds, which is quite often the case, we do a linear interpolation between a linear and a parabolic distribution by finding a K value between 1 and 2 depending upon what your period is. Okay? Or the code gives us the choice of doing a parabolic distribution as soon as you go beyond half a second period. That is a bad option. I do not know why you would take the penalty of throwing more of the forces toward the top of your building. What is the saving? A little bit of calculation, finding a K value between 1 and 2 doesn't make any sense. So that option I would strongly suggest you never use. Now, when we distribute the design-based shear, as I say, we end up with lateral forces at the various floor levels. Those are denoted by capital F sub whatever, X for floor level X, capital F sub X. Okay? Now, story shear. Story shear in any story is the sum of the forces above the story. So story shear here would be that the 3 forces. The story shear here would be the sum of 1, 2, 3, 4, 5, 6, 7 forces. And the story shear in the bottom story would be the base shear. Okay? The story shear acts through the center of mass. Now I am showing here a building, hypothetical building, not so impractical, that has in the up and down direction 2 frames on the 2 perimeters and 3 shear walls in the interior. The shear walls are of different lengths. Now, the story shear, as I said, acts through the center of mass. The center of mass would be pretty much at the geometric centroid because the mass of a structure are mainly in the floors and the roof. The walls and the columns account for very little of the mass of the structure. So the fact that this shear wall is so much longer than that shear wall does not move the center of mass from the geometric centroid, not appreciably. Okay? So the story shear acts through the center of mass. The resistance to the story shear acts through the center of rigidity. This shear wall being so much longer is way more rigid than the short shear wall. The rigidity depends on the cube of the length. Okay? So the fact that that shear wall is so much longer will pull the center of rigidity to the left of the centroid. Now we have an eccentricity between the center of mass and the center of rigidity, and that will cause a torsion. Okay? So this torsion is now being called the inherent torsion. This is the actual torsion that we have. This slide is the only time I will talk about a very important topic because you know, I will probably have talked 2 hours by the end, but we can only skim the surface in 2 hours. So many important things I'm leaving totally out. Diaphragm design is a huge topic that I could profitably spend 45 minutes on, and those would be very good 45 minutes. But anyway, so we talk about rigid diaphragms, flexible diaphragms, and somebody today, I forget who, asked me about semi-rigid diaphragms. Okay? So rigid, flexible, semi-rigid, etc. First of all, what is a diaphragm? We have slabs in our building. Slabs, am I already when you wanted me to, sorry, let me see. Give me 15 minutes, okay? Is that okay? sorry, I don't know what. Okay, no, okay, let me just, okay. So what I was saying is a slab carries gravity by out of plane bending. Okay, it bends out of plane under gravity. When the same slab is subject to lateral forces due to wind or earthquakes, the slab now bends in its own plane, not out of plane. And now the slab is acting as a diaphragm. Okay? So when we talk about diaphragm rigidity, we are talking about in-plane rigidity. Somebody was asking me about flat plate, which are thin slabs, 8 inches maybe. Are they automatically flexible diaphragms? No. In plane, they may be very, very rigid. Out of plane, they are flexible, but in plane, they are not. A solid 8-inch slab has tremendous stiffness, unless the span is very big compared to the depth. Okay? So in plane rigidity, keep that in mind. So if not if, the way it goes, ASCE 7 defines flexible diaphragms. And I wouldn't go into the definition, I don't have the time, but it is precisely defined. It can be prescriptively defined, it can be defined by calculation. It also defines prescriptively rigid diaphragms, that is no rigid by calculation. And a diaphragm that is neither flexible nor rigid, ASCE 7 considers to be semi-rigid. In the code world, when we go from ASCE 7 to IBC, any diaphragm that is not flexible, we have always considered that to be a rigid diaphragm. Okay? And if you do that, I personally don't find a lot wrong with that. Now, if a diaphragm is rigid, then the story shear will be distributed among the 5 resisting elements in proportion to their relative lateral rigidities, how much force it takes to impart unit interstory displacement to the frames and the shear walls. If, on the other hand, the diaphragm is flexible, then the distribution of the story shear to the resisting elements will be in proportion to the tributary areas. So whether the diaphragm is rigid or flexible makes a huge difference in how the lateral forces are carried by the various resisting elements. So this in itself is a very, very important topic. Also, rigid diaphragms can transmit torsion. If the diaphragm is flexible, it cannot transmit torsion. Okay, then well, I was going to say that problem goes away. It does, but it may cause other problems. Okay? So anyway, so then if the center of rigidity and the center of mass coincide, if the 3 shear walls are of the same length, now we have no inherent torsion. We must still consider an accidental torsion equal to the story shear multiplied by 5% of the plane dimension perpendicular to the story shear. Okay. Accidental torsion. There was a time, for somebody of my vintage, there was a time when we used to design for actual torsion subject to a minimum of the accidental torsion. Those days are long gone. We have been designing for many, many years for actual torsion plus accidental torsion. It is not subject to a minimum of. It is actual torsion or inherent torsion plus the accidental torsion. Okay? Now, if you have torsional irregularity, type 1A or 1B, it is not only actual torsion plus accidental torsion. We design for actual torsion plus the accidental torsion amplified by a factor that can be up to 3. This factor is given in ASCE 7B and BC. I wouldn't go into detail, but it can be up to 3. So if a building is highly torsionally irregular, there is a huge penalty. There is a point at which you will not be able to design it. And that is the intent. We don't want you to be able to design it. we want you to change the configuration. Okay? So, anyway, this is not the final, but one before the final. I had other things, but I wouldn't go into. But this is an indispensable part of seismic design, what I'm now coming to. Okay? Drift check, as we loosely call it. So, we elastically analyze our structure under four prescribed seismic forces. We calculate these delta sub XC displacements at the various pore levels, elastically computed deflections. We amplify those delta sub XC by the deflection amplification factor C sub D. But a very important detail is while we multiply by C sub D, we also divide by the importance factor I. That is because our drift limits against which we will take this, the industrial drift, are a function of the occupancy of the structure. In a hospital, our drift limit is 1% of story. Yeah, but no, I was saying it right. When there is time pressure, it causes, anyway. So in a hospital, the drift limit is 1% of story height. In an office building, it is 2% of story height. Drift limit is a lot tighter for the hospital than for the office building. And the idea here is that we shouldn't penalize the hospital twice. Once by instituting a tighter drift limit, a second time by calculating larger deflections for the hospital, because the forces under which we are calculating the deflections are augmented by an I factor larger than 1. So we take the I factor out of the deflection computation. Making sense? We do not want to calculate deflections under forces amplified by an I factor larger than 1 and at the same time institute or impose a tighter drift limit on a hospital. Okay? So this deflection, elastic value amplified by C sub D divided by I sub E at the top of a story minus the same deflection at the bottom of the same story is the inter-story drift that has to be kept within tolerable limits. Okay? Every detail is important. Every detail is important. The drift limits, as I said, 1%, most of the time you will be here, all other buildings. 1% of story height for hospitals, 2% for risk category 1 or 2, 1.5% for schools. Now, those are masonry, I wouldn't worry about. This one is kind of interesting. So buildings less than 4 stories in height, other than masonry, with non-structural elements designed to accommodate story drift. ASCE 7 has chapter 13, design of non-structural elements. Most engineers I know would take the point of view, if I have designed my structure by chapter 13, I have designed to withstand the effects of deflection as said here. So they will allow 2.5% rather than 2% of story height. I'm just pointing it out. That has become kind of standard practice. But it is only for lower buildings. Okay, final topic. Let me go here and I'll come back. I will not go into all of that. We have designed load combinations in the code by which we combine the effects of earthquake forces with the effects of gravity, effects of wind with the effects of gravity, and so forth. Okay? Now, we call these load combinations, they are not load combinations. That's the first thing I want to absolutely emphasize. Gravity loads act vertically downward on a building. Wind acts sideways. How do you combine? You cannot combine, we don't combine, we have never tried to combine. Gravity causes bending moment, shear forces, axial forces, and critical sections of numbers. So do wind forces, so do earthquake forces, and those are the things we combine. We combine bending moment due to gravity, bending moment due to earthquake, bending moment due to wind. Shear forces due to gravity, shear forces due to etc. So we are combining internal forces caused by external loads or load effects. That is very, very important to understand. We never ever combine loads. Okay? Now these are the, as I said, design load combinations of the IBC. The earthquake effect E, earthquake effect E is here, okay, in two load combinations. This one is I'm going to call it, not this one, here, this one. This is the additive seismic load combination where gravity effects add to earthquake effects. Gravity causes negative bending moment, earthquake also causes negative bending moment in the same section. This is counteracting. The gravity now counteracts earthquake effects. Gravity causes negative bending moment, earthquake causes positive bending moment. If we want to figure out the largest positive or the lowest negative bending moment, we would use the counteractive load combination. Okay? 90% dead plus 1.0 E, which is actually minus 1.0 E because it can be both directions. Now, the earthquake effect E when we analyze the structure under the code prescribed seismic forces, the bending moment, shear forces, etc. that we get at the critical sections is not E. It is denoted by Q sub E. Bending moment in a beam section is Q sub E, shear in a beam is Q sub E, axial force in a column is Q sub E, generic notation. And that is part of the earthquake effect E. To go from Q sub E to E, we have to do two things. We amplify Q sub E by redundancy factor rho, which is either 1 or 1.3 these days. And that is a topic in itself, how you calculate it and so forth. But basically, if a structure is non-redundant, rho is 1.3. If it is redundant, it's equal to 1. So we amplify Q sub E by rho, and then we add or subtract the vertical earthquake effect, which can be taken as 20% of the short period design acceleration S sub S times Q sub E, times the design dead load D. Okay, everybody with me? Rho times Q sub E plus or minus 0.2 S sub S times D. Now, how does it work? Well, VNBC has for vertical earthquake effect this expression. And this is exactly equal to what we have in ASCE 7. I put it on paper, you can follow it very easily. Exactly the same. It looks different. Now, in the additive load combination, additive seismic load combination, we would write E equal to rho times Q sub E plus 0.2 S sub D S times D. And then if we collect terms, what we have done is increase the dead load factor from 1.2 to 1.2 plus 0.2 S sub ds. If S sub ds is 1, our load factor now is 1.4 on the dead load, not 1.2. In the counteractive load combination, 90% dead plus 1.0 E, we would write E equal to rho times Q sub E minus 0.2 S sub ds times D. That would make the dead load factor equal to 0.9 minus 0.2 S sub ds. So if S sub ds is 1, our dead load factor is now 0.7 rather than 0.9. We are depending on 70% of the dead load to counter that earthquake effect than 90% of the dead load. So in the additive seismic load combination, we increase the dead load factor by considering vertically downward earthquake effect. In the counteractive load combination, we decrease the dead load factor by considering vertically upward earthquake effect, because in each case that is the conservative thing to do. Okay. This is pretty much as far as I would go. There is special seismic load combination that I'm going to skip. Final thing, this I have covered. So let's take a minute to kind of put it all together. Okay. So we start with the mapped quantity is S sub S, S sub 1, indicative of seismicity at the site. We figure out the soils at the site. From that, we can get to the design by shear. We distribute it along the height of the structure in the manner described by the code. We then carry out an elastic analysis of the structure under those distributed forces. That elastic analysis gives us the Q sub E. That Q sub E amplified by the redundancy factor rho with 0.2 S sub ds times d added or subtracted will take us from Q sub E to the earthquake effect E. And using the design load combinations, we will combine that E with the effects of gravity. Okay? There are also wind plus gravity load combinations. And we have to design the structural members for all the load combinations, gravity only, gravity plus earthquake, gravity plus wind, so forth. Okay? But then that is only part of the story. This I want to emphasize. Because we are designing for earthquake forces so low, because we are deliberately allowing inelasticity in our structural members in the design earthquake, we have to do proper detailing to make sure that inelastic deformability will be in excess of the inelastic deformations we are allowing. So that's where the detailing requirements come in. Okay? We have 3 levels of detailing: ordinary, intermediate, special. Detailing requirements are given in ACI 318. Okay? The editions change. In VNBC, you will find them in section 8.3. Chapter 8 of part 6 is detailing of reinforcement. 8.3 seismic detailing. Okay? That is exactly ACI 318 stuff. So you design for strength by chapter 16 of the IBC, section 2.5 of the NBC. You do detailing by ACI 318 or section 8.3 of the NBC. The bridge between the force and the detailing is the R value. The higher the R value, the lower the strength. Then we need, if the strength is low, we need, if we use an R value of 8, we have to do fancy detailing. We have to do special detailing. If we do an R value of 4, we might get away with ordinary detailing. So very last thing, promise. This is the very last thing I would say. Seismic design in its very essence is a trade-off between strength and inelastic deformability, as I have been saying. But an unrestricted trade-off is not allowed by our codes. If our seismic design category is B, the trade-off is unrestricted. We can do an ordinary moment frame R value of 3 and ordinary detailing. Or we can do an intermediate moment frame R of 5, intermediate detailing. Or we can do a special moment frame, take advantage of the high R value, but we have to now do special detailing. When all 3 are allowed, the ordinary detailing option is invariably the cheapest option. High strength, low ductility. If our design category is C, intermediate detailing is minimum. We now cannot do an ordinary moment frame by taking the penalty of an R value of 3, not allowed. If the design category is D, the minimum detailing is special. We do not have the choice of intermediate or ordinary detailing by taking the So it is trade-off between strength and inelastic deformability. It's a two-part affair, but it is not an unrestricted trade-off. Okay, thank you very much. Sorry to have taken so much time.
ধন্যবাদ ডক্টর এসকে ঘোষ। প্রবন্ধটা অনেক দীর্ঘ ছিল, তারপর আমাদের অডিয়েন্স মনে হয় ক্লান্ত হননি, সেজন্য আবারও ধন্যবাদ তাদেরকে। এবার সম্মানিত আলোচক বৃন্দের আলোচনা। প্রথমেই I would like to request Mr. Dr. Eric Moses, Team Leader Package S7 of URP Urban Resilience Project, Raju, and RTI International. Please, Dr. Eric Moses.
Assalamu alaikum. Good evening. First of all, I would like to express warm thanks to Engineer Sabour, President of IEB, to the distinguished members of the panel, distinguished members of the audience, and I have a promise that I will keep, which is to stick to 10 minutes of the presentation.
Thank you.
I will ask you the question and I will give you the answer. Do you know who in this audience has learned the most tonight? Well, I am the happy one. The reason is because you are engineers in that discipline. I'm also an engineer in a different discipline, and that is computer science and information technology. So this speech is going to be a little bit in between. Let me start by giving some background, sharing some background about the Urban Resilience Project. And as Dr. Ghosh has explained a moment ago, that project overarches 10 sub-packages or more. The S9 package for the revision of the Bangladesh National Building Code, and another package for establishing an online electronic construction permit system for Rajani Undayan Kampipaka, known as Rajuk. So I'm going to give you an overview of where we are now in terms of engineering, because we're talking about engineering, that is software engineering, of the future electronic construction permitting system. One of the goals is to make the city of Dhaka a role model of urban resiliency that includes the BNBC and its the compliance, its enforcement, and providing Rajuk with an electronic construction permitting system. There are sub-goals, there are important objectives to it. One is simplifying and streamlining the construction permitting processes. Another one is cost and time, making the application and the processing less costly and quicker, faster. The other one is, of course, monitoring and the quality control, so the depth and breadth of quality control over the construction process, and all that resulting into safer buildings, and that's what the reason why we are attending this seminar this evening. I have 10 slides, 3 of which have not even equations, but variables, just to connect with the presentation by Dr. Ghosh a moment ago. This is the value proposition of this e-system to key stakeholders, and to begin with, the citizens and the Bangladeshi citizens and the residents of the city of Dhaka city. Value proposition to them is just provide them with a safe and healthy environment, because building will be then resilient to seismic risk, and also resilient to other types of risk. For the real estate industry, well, they want any investor any market will want some good market environment. It means actually resilient building. It means buildings which comply with the BNBC, the Bangladesh National Building Code. And that compliance will be strengthened thanks to the ECB system. Should the Ministry of Housing and Public Works, which is a parent ministry to Rajuk, contribute to the socio-economic development of the city of Dhaka, the Dhaka city, and thereby the whole country, for the very reasons that I just shared with you. And for Rajuk, to to help the city of Dakar become a role model of urban resiliency. There is one segment missing, which is to engineers. Well, I've devoted a full slide regarding benefits to engineers. So what will this ECP system will bring to engineers in terms of benefits, in terms of changes of practices? This is what I'm going to explain now in one slide. So I've singled out 6 important points. Well, first and foremost, and that's the reason why we are here this evening, it will support the NBC 2017. And in fact, the design of that system is such that it is not aligned on the current BNBC currently in force. It is already aligned to the future BNBC, that is 2017. I will explain how in a moment, on the next slide. Something that is really new and that is really important to this audience, that for the first time in Rajuk history and development control processes, well, those will integrate structural checks, which means that the development control officers will actually perform simple, I insist on simple structural checks. I will again explain in the next few slides how that will work. One more benefit that is gained directly out of using an electronic system is direct submittal of information, plans, engineering, design documentation. Whenever that kind of documentation will be required or requested by Rajuk, the engineers yourselves who are appointed on a given development project will have the ability to submit directly that document. Not only direct, but also safe submittal, because we will affix digital signature and electronic signature to the document, which means that any attempt tampering with the content will be detected, which means that this is a guarantee, an insurance for that document to reach Rajuk in the exact same shape and form and content. One more benefit is an effective communication between engineers and Rajuk development control. In case there are clarifications required, then there will be online notification. Online in the system, or even the engineers will receive an email, and will be able again to log in the system, to type in the clarification, and that will be immediately available to the authorizing officer and the committee. So that will then help expediting and accelerating the whole process of the construction permitting application. Another benefit is processing time of application, construction permitting applications, that will be shorter, so shortening them, just because of streamlining of processes and assisting them with the electronic system. And last, but certainly not least, this will imply a closer collaboration between engineers and Rajuk. So that goes, and I will explain how in a minute. So, in fact, in a second, because I'm now turning to this slide, which explains about the scope, which is a presentation of the scope of that electronic construction permitting system. Continue. Land use clearance, plan approval. So plan approval is the stage at which structural checks will be performed. The construction permit per se, and there are 2 cases distinguished between, which are standard project and special project. Plinth level notification, monitoring as in construction monitoring, and occupancy certificates. Those are all the processes which are covered and defined in the BDMALA 2008. In addition, there will be additional capabilities, and those are listed here. Direct submittal, which I've explained already, tracking, notification, tracking meaning the ability for any applicants to know exactly the stage of process of the application, electronic signature, I mentioned, electronic fund transfer, statistics, reporting, security, reliability, performance, audit trail. I made a promise which is executed in 10 minutes. Now, I'm going to, this is the standard slide, and I've added 2 or 3 more slides for yourselves. This is how the structural checks will be integrated. There will be an additional tool called Fast Automated Simple Checks, the FASP tool, whereby the applicant, meaning typically the architect, right, will have to enter a long list of input variables that have to do with weight, that has to do with columns, that have to do with shear walls, and so on and so forth. I will show you the list of variables just after in the next slide. And then the equations that Dr. Ghosh was referring to, the equations which are mentioned in the BNBC 2017, will be programmed, and are already, in fact they are already programmed in the prototype to run the calculations and to define boundaries. So on the basis of this input variable, and thanks to the equations which I cannot decipher because I'm not on the field, then the inference engine of the program, so to speak, will be able to determine whether the design is sound or not sound. This is based on the equation, the same equation that you see before. Just to give you a bit of an idea of the input variables, well, here is a list, right? This is for column check. So there is one area of this structural check, which is column checks. Building height, first floor height, long dimension, short dimension, number of columns, long direction, number of columns in the short direction, column size, X direction, Y direction, area of steel, each facing long direction, area of steel, each facing short direction, concrete strength, performance yield, area of column ties, at build height of column, spacing of column ties, at build height of column, base shear, building weight. Please do not ask a technical question. There are 2 reasons why I'm not providing the equations. The first reason because, first, I'm not an engineer like you in that particular discipline. The second reason is that we are still in the process of validating the software design, which means that we are still in the process of validating which equation we are going to use exactly. So at that stage, we will wait validation, and then we will publish. In fact, the system itself will explain the theory behind the checks. Think of it as a decision support system. If you're familiar with IT, it's a decision support system. Something that will assist the development control officer to make the decision. This structure design, this structure design is safe and sound, or it's not. We talked about wall checks, we talked about shear walls. I mean, when I say we, it was Dr. Ghosh. These are the input variables: length of wall, thickness of wall, height of wall, area of horizontal reinforcing steel, spacing of horizontal steel, area of vertical reinforcing steel, spacing of vertical steel, overturning moment, area of reinforcing steel, end of the shear walls. There's more number of walls in X direction, number of walls in Y direction, axial load in wall, base shear in Newton, concrete compressive strength in Newton per square millimeters, rubber yield strength in Newton per square millimeters, and nearly finished, number of reinforcing steel layers, resisting moment. What I'm sharing here now is an illustration. That is not the definitive algorithm. That is the first step in a long journey. When I said that I was the one to learn the most, I repeat it. What I learned from Dr. Ghosh at ASCE is that this is going to be a very long journey, and here we're taking the first step of it. The good news is that I'm 3 slides from the finishing. There will be a second innovation integrated to the electronic construction permitting system, which is remote sensing. This is where the collaboration between engineers and inspectors, building construction inspectors, will happen. Please listen to this because this is important for the whole industry. Imagine engineers, right, who are involved in a construction project, right? But you will be provided with the ability to download in your own tablet computer, to give a tablet computer or smartphone. You will be able to download and install an application. That application will then instruct how to do monitoring by yourself. So think of it as transforming the role and adding more role to the engineer in terms of turning yourself as an inspector, which means compiling an inspector report at every level of the building. Ground level, and then first floor, second floor, up to the top. And each time using that software to actually take photos, add notes, compile it as a report, applies digital signature, submit to the ECP system, which will then be integrated in the database and checked by the inspector. According to the review of that of that report, then the authorizing officer may then decide to send an inspector for complementary information. When they send an inspector, that inspector will be equipped with a tablet and a laser measuring device and a number of programs on the tablet, including the same FRCM program. And also plan visualization and so forth. So the message here, very important message here, is that the monitoring will be strengthened. By the time we deploy this ECP system, the graduate development control officers and inspectors will be empowered in their duty when they perform inspections. That is to support the BNDC and its enforcement. This is my last slide. That's a good news. And that's a timeline. So I've used the future tense, will, because the end of the arrow is September 2020, September next year. So a number of steps. The next important step is on the 9th of July, and please save the date, because we will send an invitation, President Sabor, we will send an invitation to the IEB. On the 9th of July, there will be a demonstration of the prototype, the first prototype. IEB is invited, IAB is invited, Rehab will be invited, the professionals who are direct stakeholders to electronic construction permitting will be invited. This will be the very first prototype demonstration workshop. There will be a second demonstration workshop in October and a third in January or February. This brings my presentation to an end. If you are interested, I will show you one more thing, which is the prototype itself, so that you can see that it exists. Here, as you can see, building details, floor load, columns, shear walls, foundation, architectural information, and fire protection. This is the prototype of the FAST tool, the structural check tool. And this is how it works. It demonstrates the process of adding data. This is all the data that the applicant will add before the system will actually assist the decision with pass and not pass. So in a second we will see the report. You can see here the report of this structural check automated structural check, which is the very basis of the decisions by the authorizing officer and inspector. There is again a report, and that's it. That report is integrated. Again, I thank you very, very much for your attention.
Thank you, Dr. Eric Mose, Team Leader, Package S7 of URP Raju. এই মুহূর্তে সম্মানিত আলোচকবৃন্দের মধ্যে থেকে আলোচনায় অংশগ্রহণ করতে অনুরোধ করছি অধ্যাপক ডক্টর প্রকৌশলী রাকিব আহসান, অধ্যাপক পুরকৌশল বিভাগ UA।
ধন্যবাদ মাননীয় চেয়ারম্যান, মাননীয় প্রধান অতিথি, আলোচকবৃন্দ এবং মাননীয় অতিথি, সবাইকে শুভ অপরাহ্ন। আমি আসলে জানতামই না যে আমি আজকে ডিসকাশন প্যানেলে আছি। যাই হোক, আসলে এখানে কোড তৈরি করার সময় অনেকের অবদান ছিল, তাদের অনেকে আমি সামনে দেখতে পাচ্ছি। আমি কয়েকজনের নাম না বললেই না। আমাদের মধ্যে এই আর্থকুয়েক লোডিং এর চ্যাপ্টারটার মেইন যে কন্ট্রিবিউটর প্রফেসর হামিদ মালিক হুসাইনি আমাদের মধ্যে আছেন। আমি এরপরে অনুরোধ করবো যেন স্যার এই ব্যাপারে কিছু বলেন আজকের আলোচনা প্রসঙ্গে। আমি দেখতে পাচ্ছি ইঞ্জিনিয়ার মুজিদ শিকদার সাহেব, আমি দেখতে পাচ্ছি ইঞ্জিনিয়ার সাদুল রহমান সাহেবকে, পিডব্লিউডি থেকে ইঞ্জিনিয়ার রফিকুল ইসলাম, এনারা সবাই আমাদেরকে ভীষণভাবে সাহায্য করেছিলেন এই লেখার সময়। তো ওনাদের অত্যন্ত মূল্যবান বক্তব্য থাকতে পারে। আসলে আমি খুবই সংক্ষেপে আমার ডিসকাশন শেষ করব। আমি আশা করব যে আলোচনা পর্বে প্রশ্ন আসবে। তো যেটা হচ্ছে যে আমি খুবই আমাদেরকে ভাগ্যবান মনে করছি যে ডক্টর হোসেনের মতো একজন প্রথিত যশা ইঞ্জিনিয়ারকে আমরা পেয়েছি বাংলাদেশে এই প্রজেক্টে, যিনি আমাদেরকে এইভাবে আমাদের যে ASCE 7 বা IBC সম্বন্ধে আমাদেরকে জানাতে পারছেন। আমাদেরকে কোডের ইন্টারপ্রিটেশন সম্বন্ধে আমাদের প্রায় বিভিন্ন রকম প্রশ্ন থাকে, সেগুলো সরাসরি তার কাছ থেকে জানতে পারছি, জন্য আমরা আসলে নিজেদেরকে খুবই ভাগ্যবান মনে করছি। এখানে কতগুলো ব্যাপার আমি খুব ছোট করে বলবো। এই যে পুরো যে আয়োজনটা, যে এই আমাদের বিলিং কোডের ইমপ্লিমেন্টেশন এনফোর্সমেন্ট, বা এই যে আমাদের যে নতুন সফটওয়্যার আসছে ডক্টর যে দেখালেন, এগুলো সবই কিন্তু ভিত্তিটা হচ্ছে BNBC 2017, মানে বিলিং কোড 17। এইটা এখন অ্যাপ্রুভ হন। এইটা যদি অ্যাপ্রুভ না হয় তাহলে এই সমস্ত আয়োজনই ব্যর্থতায় পর্যবেসিত হবে। আমি একটা খুব ছোট উদাহরণ দিয়ে বলছি। আজকে বিকালে আমরা একটা মিটিংয়ে ছিলাম, রূপপুর পাওয়ার প্ল্যান্ট, নিউক্লিয়ার পাওয়ার প্ল্যান্টের মিটিংয়ে। আমরা মিটিংয়ে যারা ছিলাম তারাও এখানে আছেন। সেখানে একটা মূল ভিত্তি, আমাদের যে নিউক্লিয়ার পাওয়ার প্ল্যান্ট হচ্ছে সেইটা ডিজাইনের একটা মূল ভিত্তি হচ্ছে রূপপুরের অবস্থানটা বাংলাদেশের ম্যাপে। আমাদের 2006 এর বিল্ডিং কোড অনুযায়ী রূপপুরের অবস্থান হচ্ছে জোন 1, সবচেয়ে কম অ্যাক্টিভ সাইসমিক জোন, যার ফলে সেখানকার ডিজাইন এক্সেলারেশন অনেক কম ধরে সেটা করা হচ্ছে। কারণ হচ্ছে যে সেটি লিগাল 2006 এর কোড, কিন্তু BNBC 2017-এ রূপপুরের অবস্থান হচ্ছে জোন 2-তে, যেখানে আমাদের আরো বেশি অ্যাক্সেলারেশন ধরা উচিত, কিন্তু আমরা ধরতে পারছি না, কারণ এটা অ্যাপ্রুভ হয়নি। এটা অ্যাপ্রুভ হলে এখনো আমাদের সেটা কারেকশনের সুযোগ আছে, কারণ এখনো ডিজাইন কাজ চলছে। এটা একটা এক্সাম্পল দিচ্ছি যে কতটা ইম্পর্টেন্ট আমাদের এই বিল্ডিং কোডের অ্যাপ্রুভালটা। এখানে আমাদের অনেক বিষয় আছে। আমার ধারণা ডক্টর ঘোষ আর অনেকগুলো লেকচার দিতে পারেন আমাদের এই বিষয়গুলো নিয়ে। বিশেষ করে আমাদের 2017-এ যেখানে ডক্টর ঘোষের প্রেজেন্টেশনের সাথে একটু তফাৎ হবে এক জায়গায়, যে আমাদের ডাইনামিক অ্যানালাইসিসের রিকোয়ারমেন্ট। BNBC-তে কিন্তু এই রিকোয়ারমেন্টটা ডক্টর ঘোষ যে ফ্লোচারটা দেখালেন তার থেকে অনেক বেশি স্ট্রিক্ট আমাদের BNBC-তে। সেখানে আমাদের জোনের প্রসঙ্গ আছে, সেখানে আমাদের সাইট ক্লাসিফিকেশনের প্রসঙ্গ আছে এবং যথেষ্ট স্ট্রিক্ট, যার ফলে আমাদের BNBC 2017 অ্যাপ্রুভ হওয়ার পরে আমাদের বেশিরভাগ ইঞ্জিনিয়ারকে ডাইনামিক অ্যানালাইসিস করাটা জানতে হবে, যেটা আমাদের কিছুটা উইকনেস আছে আমাদের ইঞ্জিনিয়ারদের মধ্যে। তো এটা একদম ইম্পারেটিভ যে ডাইনামিক অ্যানালাইসিসটা আমরা ঠিক মতো জানবো। সেখানে রেগুলেটরি ব্যাপারগুলো বুঝতে হবে। আমাদের বেশিরভাগ অ্যাপার্টমেন্ট বিল্ডিং সফট স্টোরি হচ্ছে, সেটা বুঝতে হবে। ইনফিলের স্টিফনেস আমরা কিভাবে নিব সেটা আমাদের বুঝতে হবে। তো এই জিনিসগুলো খুবই জরুরি, যেমন সাইমালটেনিয়াসলি এক্স এবং ওয়াই ডিরেকশনে আমাদের অ্যাক্সেলারেশন ফোর্স দিতে হবে, এবং এক্সেন্ট্রিসিটি যেটা ব্যাপার বললেন সেটাকে কিভাবে বাড়াতে হবে, এই জিনিসগুলো ভার্টিক্যাল কম্পোনেন্ট নিতে হবে। এই জিনিসগুলো আমাদের ডিজাইন ইঞ্জিনিয়ারদের মধ্যে ক্লিয়ার হতে হবে, যেটা আমরা এখন প্র্যাকটিস করছি না। এখানে যেটা পিরিয়ডের ব্যাপারে আরেকটি জিনিস, যেটা আমরা কিন্তু ইনফিল ওয়ালের পিরিয়ডটা, ইনফিল ওয়াল থাকলে পিরিয়ড যে আমাদের কমে যাবে সেই ব্যাপারটা কিন্তু আমাদের চিন্তা করতে হবে, এবং সেই ক্ষেত্রে কিন্তু আমাদের ফোর্স বাড়বে। এবং ওই আমাদের শেয়ার ওয়াল, এখন আমাদের উঁচু বিল্ডিং হচ্ছে, শেয়ার ওয়াল আমরা ব্যবহার করছি। শেয়ার ওয়ালে যে আমাদের ড্র্যাগ রেইনফোর্সমেন্ট, কালেক্টর রেইনফোর্সমেন্ট দরকার, আমাদের রিজিড ডায়াফ্রামের জন্য যে কর্ড রেইনফোর্সমেন্ট দরকার, এই নতুন নতুন জিনিসগুলো কিন্তু আমাদের জানতে হবে। আর একটা ব্যাপার নিয়ে আমাদের কনফিউশন আছে অনেকের মধ্যে, যেটা ডক্টর ঘোষের কাছ থেকে আমরা ভবিষ্যতে আরো ক্লিয়ার হতে চাইবো, সেটা হচ্ছে যে ই এর ভ্যালু যে আমরা রিডিউস করি, কখন ক্র্যাক কনসিডার করে রিডিউস করবো, কখন করবো না, ইত্যাদি একটা কনফিউশন আমাদের মধ্যে আছে। তো এই জিনিসগুলো আমাদের সামনে আমার মনে হয় আমাদের আরো জানার প্রয়োজন হবে। তো এই অ্যাওয়ারনেসটা তৈরি করাটা খুবই দরকার ছিল। এটা আমার মনে হয় আজকের অনুষ্ঠানটা খুবই সুন্দরযোগ্য হয়েছে। ধন্যবাদ।
আমি খুবই দুঃখিত যে আমাদের সেমিনারে এই পর্বে আমাদের প্রশ্নোত্তর পর্ব থাকা উচিত ছিল, কিন্তু আসলে এত বেশি রাত হয়ে গেছে যে 9টার মতো বাজে, আমরা আসলে প্রশ্নোত্তর পর্বটা রাখতে চাচ্ছি না সময়ের অভাবে। তবে আপনাদের জন্য আমার একটা প্রস্তাব আছে, অ্যাজ এ সিভিল ইঞ্জিনিয়ারিং ডিভিশনের সেক্রেটারি, আপনারা যদি এখানে আসলে মেইনলি প্রফেশনাল ইঞ্জিনিয়ার যারা রাজুক এনলিস্টেড ইঞ্জিনিয়ার, তাদের আধিক্যই বেশি, কারণ তাদেরকে আমরা স্পেশালি দাওয়াত দিয়ে এখানে এনেছি। তো তারা যদি চান আমাদের এই এক্সপার্টদের সাথে আলাদাভাবে ওয়ার্কশপ করতে, আমরা অবশ্যই আয়োজন করব, এবং যেসব প্রশ্ন আপনাদের মনে রয়ে গেল সেগুলো ওয়ার্কশপের মাধ্যমে ক্লিয়ার করে নেবেন। আমি সেই প্রস্তাব আপনাদের কাছে রাখলাম। এই পর্যায়ে আমাদের অনুষ্ঠানের বিশেষ অতিথি, আসলে এই ব্যাপারে একটু ব্যাখ্যা দেওয়া দরকার। আমাদের ব্যানারে আসলে বিশেষ অতিথির নামটা নেই, কারণ আমরা কনফার্ম হতে পারিনি যে আমাদের সম্মানিত বিশেষ অতিথি প্রকৌশলী ডক্টর সুলতান আহমেদ স্যার আমাদেরকে আসলে সময় দিতে পারবেন কিনা, সে কারণে ব্যানারের নামটা নেই। তারপরেও স্যার এসেছেন, আমরা স্যারের কাছে কৃতজ্ঞ। সিভিল ইঞ্জিনিয়ারিং ডিভিশন আইবি পক্ষ থেকে তাকে ধন্যবাদ জানাচ্ছি এখানে আসার জন্য। এখন আমাদের সামনে বিশেষ অতিথি হিসেবে বক্তব্য রাখবেন ডক্টর প্রকৌশলী সুলতান আহমেদ, চেয়ারম্যান রাজু।
ইনস্টিটিউট অফ ইঞ্জিনিয়ার্স বাংলাদেশের সিভিল ইঞ্জিনিয়ারিং ডিভিশন থেকে আয়োজিত আজকের এই Seismic Design by ASCE 705, the basis of Seismic Design by BNPC 2017, এই সেমিনারের সম্মানিত সভাপতি ইঞ্জিনিয়ার Mohammad Habib Rahman, and chief guest of this seminar, my friend Professionally Engineer Mohammad Abis Sabur, and other distinguished guests on the dais, and especially I would mention Dr. Swapnendra Kumar Ghosh, a legend and a renowned civil engineer, and my teacher in front in the court, Professor Shamil Boshonia, left. I convey my sincere gratitude to him. And very renowned engineers, civil engineers in the room. Assalamu alaikum and very good evening. First of all, Rajuk is very much thankful and grateful to Institute of Engineers Bangladesh for making this room and space for delivering what Rajuk is presently going to do in future under Urban Resilience Project, and especially for inviting Dr. Ghosh for very skillful and very important seminar in this. And also I'm personally very much thankful and grateful to IB for inviting me, but I could not confirm it because of my other business, but my chief engineer Hilali asked me, and then I tried to find some time, but I'm very much delighted and very happy to be here with engineers again, and I learned a lot from this discussion. Thank you very much. By training, I'm a civil engineer from Kuwait, and just to say that maybe I'm an exception that I studied Kuwait for 3 times. My undergraduation, my master's, and also my PhD I pursued from Kuwait, and you can understand, and you should have confidence on my resilience that I have gone through Kuwait for 3 times. And my present job is to take Raju forward. I'm very much confident that I am capable of, I have the ability from both sides, from technical and also from administrative point of view, to take the very renowned organization, one of the, top level organization in the country, Raju, to take it forward. And I have got every support. I joined Raju less than a month, but I have got every support from Raju engineers and Raju professionals. And I am very much grateful to Raju as a whole. I never forget half FCK's ABD square, or ASFHC, that is a civil engineer. I always tell me half FCK's ABD square, not a civil engineer, because this is the Bible for civil engineers. And I did not forget, though by profession I am doing some administrative job, but still I pursued my education, higher education in engineering. And my PhD is also an engineering PhD, remember. What I am saying that presently what we do as a construction permit, we only check dimensions. And at this point of time, Raju is only checking dimensions. The setback, whether the room is okay or not, but do not check, cannot check the reinforcement, cannot check the structural rigidity or strength of a structure. And I think the Urban Resilience Project has come up with very, very good solutions. We will be having our X-ray eyes. The machine will have X-ray eye. And when we put it in a column, when we put in a beam, or when we put on a slab, it will tell about the steel reinforcement. And then my people will be able to see whether they put it before an occupancy certificate is issued. We will be able to check the structural stability and the stiffness and rigidity, whether it is constructed as per the design, or the design that is submitted by an engineer and an architect is also structurally sound. We will be able to do that. And Urban Resilience Project is going to give us that kind of software and solution. And I think at this point of time, as a civil engineer, we have the responsibility to check and structure, a civil engineering structure, whether it is structurally safe or not. And other paraphernalia are there, but first of all, structure. I think as Dr. Eric presented here, that electronic construction permitting and other software will provide us this thing. But presently, again, in this first phase, first version of the electronic construction permit will only help us to identify the dimensional things, but not the structural things. But in coming future, in version 2 or version 3, maybe Raju will be able to check structurally the structure is whether rigid or not, whether designed or constructed as per the design. So at that point of time, I think I need support from IEB professional engineers I need support from BUET professors. I need support from other centers of excellence that are present in the country to check, to help Raju. And I already talked to my friend, president of IB, that we need a pool of professionals. Raju mobilized fund from the ordinary citizen. Raju mobilized fund from plot, some clearance, other thing. We draw our own resources from you, from people. So what is the problem to serve them in time and with quality services? I do not see any problem. I need support from IB, I need support from BUET, I need support from you engineers. And you must help Raju. And I have seen for an example that we can provide our construction permit using this electronic online submission by a week. Whereas earlier we would take 60 days or 30 days. Can you imagine a client is not coming at Raju, is submitting electronically, and we check it electronically, but in between we need to go in the field for inspection. We can do it very quickly, and then we can also check electronically, and then we can give permit. And a client must not come at Raju personally, physically. We can approve it, and we can get a print of it, we can put our sign and seal, and then we can have a scanned copy of that, and we can mail it to the client. No need to come. I want to eliminate this physical interfacing with Raju by client, and I hope that is very much possible with you people and also with the technology available presently in the country or anywhere in the globe. So Raju is very much committed. Raju is very much committed to do this. And I asked my staff at Raju, they all agree that we should go with this kind of technology and we should go with this kind of smart and electronic application of technology so that we can provide services to our client very shortly and with. But again, we need support. Presently, a certified engineer, when he designed a structure, I think he is very much careful now, as a civil engineer, a graduate civil engineer, that the structure will be a structure of its own. So we bank on that presently, but we need to check again, because an auditing and a checking will provide you more confidence as a third party, or as in between. Editing is always better by a third party. So I think at that situation, we need also support from IEB and you professional. I hope you will extend your hand for supporting Raju. Again, the BNBC 2017 is a draft, and we have submitted it to the ministry. Ministry sent it to the drafting and legislative wing of Ministry of Law. They have already vetted it, and then we will. And our honorable minister is a lawyer, and he is very much conversant with this, and he is very much straightforward. And I hope that we will be able to enact this BNBC maybe 2019 or maybe 2020, and maybe, and that will be a great. But presently, what we are following, I think the software that is coming is will be compatible enough to incorporate the changes that will come, the modification that will come in the 2017 BNBC or 2020 BNBC, whatever it is. So that compatibility in the software will be kept. So this is one thing. But though I am not doing my technical business as a professional job, but what I understand that if your structure goes beyond 12 story or 14 story, shear wall should be an imperative option for the structure, as Dr. Ghosh said. Please remember it. Please remember it. Tell your client that for seismic point of view, a shear wall is an imperative if it goes beyond 12 or 14 story. And my engineer, whether they can ask a question, where should be the shear wall position? As Professor Ghosh said, that the seismic design is a compromise between the strength and the structure or inelastic, what is deformity of the structure. There is a compromise. How much inelastic deformity you will allow with the strength of the structure itself. I think these are the Bible words you have to remember. As I have taken this point from you. So can we say what are the position, what will be the position of the columns, what will be the position of the staircase, what should be the ideal position of the lift case, what will be the ideal position of the fire escape, what will be the ideal position of the shear walls. This kind of guideline or thumb rule can help our engineers to check the structural stability of the building. I think we have learned a lot from, and again, this is, I mean, as a student, I can say that the base shear, you have to distribute all over the structure, and you have to identify the locations where you can put the structural elements that will absorb the base shear during a seismic event. So that is also very technical, that is also very important, and I think there is a lot to learn from this. I convey my sincere gratitude and thank to Professor Dr. Ghosh that he has delivered in lecture. I was just observing you so calm and quiet. Every word and every notation, every intonation you are exactly receiving, and that was a great success. And Professor Dr. Ghosh is highly blessed with a very qualified communication skill and the way he is delivering. Thank you very much, and we have very much benefited from your lecture and delivery. And I hope that within a very short period of time, Rajuk will be a totally online and digital institute or an organization, so that we can very quickly, because we have other business, we have other very important business, rather than this construction, permitting, processing, other things. We should not spend our time there. We have other business. We want a green city. We want a city of human ecosystem. We want a city of, and then at the end, I will ask what I observe from my living in a city like, I live in a 15-story building. What happened? I will go from here and I will enter into my ancestor drawer, human ancestor drawer. I will enter into my 14-story room, and then I will stop. I will shut my door, and then that is a box. And in the morning, I will get up, and very quickly I will eat my breakfast, and then I will enter into a lift case. That is also a box. Then my car is waiting. That is also a box. And I go to my office. I get down, and I also enter into another box. And then I enter into my room. That is another box. So my 24 hours is from box to box. Can civil engineer help to go away from other design, so that as an animal we are free for movement. We should not live in a box. We should have other option for living. Please think about it. So I condominium sort of thing. I suppose these are like human ancestor drawers. We put file in the drawer like we are putting ourselves in the drawers. So can civil engineers give some kind of solution based on ecosystem, based on the nature, so that we can have good living and we can look at the nature. So again, thank you very much. As the organizer saying that they can arrange other similar engineering workshop. Rajuk will be always with you, please. Rajuk will be always with you. Rajuk is not a poor organization, remember. Rajuk is a rich organization. We want to spend our money for value. We want to spend our money for good services to the client. And you can help. I think we will go together. Thank you very much for this.
ধন্যবাদ আমাদের আজকের বিশেষ অতিথি ডক্টর প্রকৌশলী সুলতান আহমেদ, চেয়ারম্যান রাজু। আমি আসলে এই সিভিল ইঞ্জিনিয়ারিং ডিভিশনের সেমিনার থেকে আর একজন ব্যক্তিত্বকে একটু ধন্যবাদ দিতে চাই। তিনি হচ্ছেন আমাদের প্রধান প্রকৌশলী রাজু খেলালি সার্কি। তিনি হচ্ছে আরবান রেজিডেন্স প্রজেক্টের প্রজেক্ট ডাইরেক্টর। আমরা সবাই মিলে তার জন্য একটু হাততালি দিই, কারণ স্যারের কারণেই আসলে আমরা এতজন এক্সপার্টদেরকে একসাথে পেয়েছি এবং পরিচিত হতে পেরেছি। তো তার সাথে যেহেতু রাজুকের চেয়ারম্যান মহোদয় আমাদের সাথে আছেন এবং আমাদের আজকের প্রফেসনালরা কোনো প্রশ্ন করতে পারেননি, সিভিল ইঞ্জিনিয়ারিং ডিভিশনের সেক্রেটারি হিসাবে তারা আসলে আমার কাছে কিছু প্রশ্ন রেখে গেছেন। তো আমি দু একটা তাদের পক্ষ থেকে প্রশ্ন রাজুক চেয়ারম্যান স্যারের কাছে করতে চাই। প্রথম প্রশ্নটা হচ্ছে, স্যারই উল্লেখ করেছেন যে আমরা আসলে প্ল্যান অনুমোদন করার সময় দেখতাম ব্যাকসেট এবং দেখতাম যে আসলে দেখতাম আর্কিটেকচারাল পার্টটা। এখন এই সমস্যাটা যখন তৈরি হলো তখন আমাদের স্ট্রাকচারাল ইঞ্জিনিয়াররা আসলে আস্তে আস্তে ব্যাক ফুটে চলে যেতে লাগলো। একসময় স্ট্রাকচারাল ইঞ্জিনিয়ারিং ফার্মগুলো হয়ে গেল আর্কিটেকচারাল ফার্ম এবং একসময় ইঞ্জিনিয়ারদের অধীনে আর্কিটেক্টরা চাকরি করতো। বাংলাদেশে রাজুকের কারণেই এখন ইঞ্জিনিয়ার স্ট্রাকচারাল ইঞ্জিনিয়াররা চাকরি করে আর্কিটেকচারাল ফার্মে, মানে আর্কিটেকচারের অধীনে, এবং রেটও তুলনামূলকভাবে আর্কিটেক্টরা আমাদের সিভিল ইঞ্জিনিয়ারিং স্ট্রাকচারাল ইঞ্জিনিয়ারদের চেয়ে প্রায় 10 টাইমস অনারিয়াম বা মূল্য পায়, ভ্যালু পায়। এই জিনিসটা আসলে রাজুকই পরিবর্তন করতে পারে। আমাদের প্রথমবারের মতোই ইউআরপি প্রোগ্রামগুলো যে মনে হয়েছে যে রাজুকের প্ল্যান পাসটা আসলে ইঞ্জিনিয়ারদের ভূমিকা আছে। এর আগে মনে হতো যে প্ল্যান পাসে শুধু আর্কিটেক্টদের ভূমিকায় আছে। এখন এইটা যত তাড়াতাড়ি সম্ভব যদি ইকুইলিব্রিয়াম না করা যায়, ইকুয়াল না করা যায়, তাহলে স্ট্রাকচারাল ইঞ্জিনিয়াররা আসলেই খুব সমস্যায়। এবং আরো একটা জিনিস, রাজুকের মধ্যে কি আসলে মানে সিভিল ইঞ্জিনিয়ারদের উপরে আপার হ্যান্ডে আর্কিটেক্ট আছে কিনা একটু ভেবে দেখার ব্যাপার আছে। কারণ আমাদের কাছে একটা চিঠি আসছে, চিঠিটা খুবই দুঃখজনক। রাজুক একটা হাইরেজ বিল্ডিং এর প্ল্যান অনুমোদনের জন্য কমিটি তৈরি করেছেন। আপনারা জানেন যে হাইরেজ বিল্ডিং মানে হচ্ছে স্ট্রাকচারাল পার্ট, কিন্তু সেখানে আমাদের আর্কিটেক্ট আইএবি থেকে 2 জন প্রতিনিধি রাখা আছে, ইনস্টিটিউট অফ প্ল্যানার্স থেকে 1 জন প্রতিনিধি রাখা আছে। আমি জানি না প্ল্যানার্স ইনস্টিটিউট অফ প্ল্যানার্স 5 জন সদস্য আছে, কিন্তু যেখানে সিভিল ইঞ্জিনিয়াররা 30,000 সদস্য, আমাদের রেজিস্টার্ড মেম্বার 50,000 প্লাস, আইবি কোনো সদস্য নাই, ইঞ্জিনিয়ারদের কোনো সদস্য। রাজুকের সেই চিঠিতে, হাইরেজ বিল্ডিং অনুমোদনের চিঠিতে আইইবি মানে ইঞ্জিনিয়ার্স ইনস্টিটিউশনের কোনো সদস্য রাখা হয়নি। এই দুঃখজনক ঘটনা আমি এই আজকের সেমিনারে রাজুকের চেয়ারম্যান মহোদয়ের কাছে উপস্থাপন করলাম এবং আমরা চাচ্ছি যে এটা আমরা কেন দরখাস্ত দিয়ে চেঞ্জ করব। রাজুক অনুধাবন করুক তাদের স্ট্রাকচারাল ইঞ্জিনিয়ার দরকার আছে কিনা, রাজুক অনুধাবন করুক স্ট্রাকচারাল ইঞ্জিনিয়ারদের হাইরেজ বিল্ডিং এর দরকার আছে কিনা, এবং হাইরেজ বিল্ডিংটা আসলে কাদের পার্ট, এটা কি স্ট্রাকচারাল ইঞ্জিনিয়ারদের পার্ট না আর্কিটেক্টদের পার্ট। যদি রাজুক মনে করে যে এখানে ইঞ্জিনিয়ারদের প্রতিনিধি থাকা দরকার, অবশ্যই তারা আইইবি থেকে, যদি আইএবি থেকে 2 জন প্রতিনিধি রাখা যায়, তাহলে আইইবি থেকে 10 জন প্রতিনিধি রাখা উচিত। এবং এই সেমিনার থেকে আমি রাজুক চেয়ারম্যান মহোদয়ের কাছে এই দাবিটুকু রেখে আমি আমাদের সেমিনারের পরবর্তী সেশন হচ্ছে আমাদের গেস্টদের জন্য। আজকে আমাদের সামান্য সম্মাননা আছেন। আমি আবারও দুঃখ প্রকাশ করছি যে আমাদের বিশেষ অতিথি কনফার্ম ছিলেন না বলে বিশেষ অতিথির জন্য আসলে আমরা কোনো সম্মাননা রাখতে পারিনি, তবে আমরা পরবর্তীতে তার কাছে পৌঁছে দেবো এই প্রতিশ্রুতি দিচ্ছি। তো প্রথমেই আমাদের মাননীয় আজকের অনুষ্ঠানের প্রধান অতিথি আইবি প্রেসিডেন্ট প্রকৌশলী মোহাম্মদ আব্দুল সবুরকে অনুরোধ করব আজকে সম্মানিত আলোচক বৃন্দের মধ্যে থেকে ডক্টর এরিক মোসেটকে তার সম্মাননা প্রদান করার জন্য। মূল প্রবন্ধ উপস্থাপনকারী ডক্টর এসকে ঘোষ। ডক্টর এসকে ঘোষকে আমাদের আইবি পক্ষ থেকে সম্মাননা প্রদান করবেন মোহাম্মদ আব্দুল সবুর। পর্যায়ে আমাদের অনুষ্ঠানে বক্তব্য রাখবেন আজকের অনুষ্ঠানের সভাপতি প্রকৌশলী মোহাম্মদ হাবিবুর রহমান, চেয়ারম্যান সিভিল ইঞ্জিনিয়ারিং ডিভিশন আইবি।
Honorable Chief Guest, this is IB, dear audience, participants, speakers and discussants, ladies and gentlemen. I on behalf of Civil Engineering Division IB convey my sincere gratitude to the keynote speaker for his nice and elaborate presentation. Bangladesh, we know there is probability of earthquake in Bangladesh, even due to its proximity to the collision boundary of the northeast moving Indian plate and Eurasian plate. There is history of earthquake of magnitude greater than 7 in Bangladesh, and epicenter is within Bangladesh. So, the designer we invited here were involved with mainly in design. So, designer should take care of earthquake. But we learned from Mr. S.K. Bush. Dr. Bush is renowned person in this arena. So we are grateful to him as he given time for us. So this, what we learn from him, this is very much useful for the design people who came here. If one likes to design or construct a building without any damage or major earthquake event, then it may not be economically feasible. And high-rise building maximum related with constructed by the developer company. If they take 25 years, 2005 years return period, the cost will be huge, and there is no, what Raju Chairman said, no checking from the government side. The developer designs and construct, they only approve the plan. So if BNBC is approved, then Raju can play a vital role to check the design. Hope that the authority will be much more vigilant so that BNBC strictly follow in designing and constructing buildings and other structures. We shall timely forward recommendation. If you have any questions, you can send it to us. We have to Secretary Civil Division, and we will send it to the keynote speaker, these questions, and we will prepare a recommendation from IEB to the proper authority for taking necessary action on this from this seminar. I am also very much grateful to the chief guest, President IEB. He has much his other works, and he is still here for a long time. I express my sincere gratitude to you, the audience. You are sitting here. One engineer came at 3 p.m. here because he knows there will be a lot of audience and I may not get a seat. He came at 3. He asked me why is the seminar. So from 3 to 9, now it's 9, more than 9. So 6 hours, or somebody is for 4 hours. So we are really grateful to you, keeping time with us. And thank you. This is duty of Civil Engineering Division. This is mostly professional. Today, it is not a seminar, basically. This is a professional listen from an expert. Design. It should be full day session, but due to shortage of time from SK, and he still can spend more than 1 hour. But we, if you spend more than 1 hour, he also can take. But we pressure reduce, please reduce. So thank you all, and with the speech of our chief guest, the session will be complete. Now I request chief guest, President IEB, Abdul Sobor, Engineer Abdul Sobor, and Secretary Science and Technology, Honorable Shahwandi, to deliver his speech. Thank you.
Bismillahirrahmanirrahim. Civil Engineering Division কর্তৃক আয়োজিত আজকের যে সেমিনার Seismic Design by ASCE 705, the basis of seismic design by BNBC 2017. শীর্ষকালীন আজকের এই সেমিনারে শ্রদ্ধাভাজন সভাপতি, সিভিল ইঞ্জিনিয়ারিং ডিভিশনের চেয়ারম্যান হাবিব ভাই, ইঞ্জিনিয়ার হাবিবুর রহমান, আজকের এই সেমিনারের বিশেষ অতিথি হিসেবে উপস্থিত আছেন আমার অত্যন্ত কাছের এবং আমার বন্ধুবর শ্রদ্ধাভাজন ডক্টর ইঞ্জিনিয়ার সুলতান আহমেদ, আজকের অনুষ্ঠানের মূল প্রবন্ধকার ডক্টর এস.কে ঘোষ, প্রেসিডেন্ট এস.কে ঘোষ অ্যাসোসিয়েট অফ আইসিসি। আমি তাকে আন্তরিক ধন্যবাদ এবং কৃতজ্ঞতা জানাই, তিনি আজকের এই অনুষ্ঠানে একটি ভালো প্রবন্ধ উপস্থাপন করেছেন। আর আমি আরো ওনাকে ধন্যবাদ জানাই যে ওনার বাড়ি কিন্তু, যদিও আমরা জানি যে ইন্ডিয়া, আসলে ওনার অরিজিনাল বাড়ি কিন্তু এই দলজন, সুতরাং সেই হিসাবে উনি আমাদের আত্মীয় বটে। আর ডিসকাশন হিসেবে উপস্থিত আছেন অধ্যাপক ডক্টর প্রকৌশলী রাকিব হোসেন, প্রকৌশল বিভাগ বুয়েট। আর উপস্থিত আছেন এরিক মাসেব, টিম লিডার প্যাকেজ S7 of URP Raju RTI International. I would like to express my sincere thanks to Eric Masek, সিভিল ইঞ্জিনিয়ারিং ডিভিশনের ভাইস চেয়ারম্যান এবং সেক্রেটারি তুহিন সহ সিভিল ইঞ্জিনিয়ারিং ডিভিশনের সদস্যবৃন্দ, আর আমার সামনে উপস্থিত আমার শ্রদ্ধাভাজন প্রকৌশলীবৃন্দ, সবাইকে আমার আন্তরিক কৃতজ্ঞতা এবং ধন্যবাদ জানাই। প্রায় 4.5 ঘন্টা যাবৎ আজকের যে সেমিনার, আমি এটাকে সেমিনার না বলে আমি এই জিনিসটাকে বলবো যে আমাদের প্রফেশনাল ইঞ্জিনিয়ারদের জন্য এটা একটা প্রফেশনাল যে এক্সেলেন্স বাড়ানোর জন্য যে একটা ওয়ার্কশপ, সেটাকে আমি বলতে চাই। এটা আরো 1 ঘন্টা যদি বেশি হতো তাহলে আমাদের প্রফেশনাল, আমার সামনে যারা প্রফেশনাল ইঞ্জিনিয়াররা আছেন তারা আরো নিজেদেরকে লেটেস্ট আপডেট করার জন্য আরো মনে হয় কাজ হতো। আমি আশা করি যে সিভিল ইঞ্জিনিয়ারিং ডিভিশন আমাদের যে বিপিআরপি থেকে যারা পিএনস পাচ্ছেন বা আমাদের আজকের যে রাজুকের সঙ্গে আমরা যারা জড়িত, ভবিষ্যতে তাদের এই প্রফেশনাল এক্সিলেন্সি বাড়ানোর জন্য যদি প্রয়োজন হয় রাজুকের সঙ্গে যৌথভাবে আমরা এই প্রোগ্রাম করতে আগ্রহী। আমি বিশেষ করে আমার বন্ধু রাজুকের চেয়ারম্যানকে আন্তরিক কৃতজ্ঞতা এবং ধন্যবাদ জানাই। উনি ওনার অনেক ব্যস্ততার মাঝে উনি এসেছেন, এই জন্য আইবির পক্ষ থেকে ধন্যবাদ জানাই। এবং ওনার সঙ্গে আমার কথা হয়েছে যে আইবি মানে আগামী দিনের একটি গ্রিন সিটি, গ্রিন বিল্ডিং করার জন্য, আগামী দিনের একটি বসবাসযোগ্য ঢাকা সিটি তৈরি করার জন্য আইবি সর্বাত্মকভাবে আমরা সাপোর্ট দেবে, এইটুকু আমরা আশ্বাস দিতে পারি। এবং আমাকে ধন্যবাদ জানাই উনি আমাদের সঙ্গে যৌথভাবে যে বিভিন্ন রাজুকের যে কাজগুলো আমাদের সঙ্গে উনি করতে চান, সেই জন্য আমি আন্তরিক ধন্যবাদ জানাই। আমরা আগ্রহী আপনার ডিপার্টমেন্টের সঙ্গে ইঞ্জিনিয়ার্স ইনস্টিটিউশন তার এক্সেলেন্স, বিশেষ করে আমাদের সিনিয়র ইঞ্জিনিয়ার যারা আছেন, যারা তাদের সহযোগিতা, আমাদের টিচারদের সহযোগিতা, আমাদের নতুন ইয়াং ইঞ্জিনিয়ারদের এখানে ইন্ট্রোডিউস করা, যাতে ফিউচার আমাদের এক্সেলেন্সকে ধরে রাখার জন্য সেই থেকে আমাদের সর্বাত্মক চেষ্টা অব্যাহত থাকবে ইনশাআল্লাহ। আমি রাজুককে ধন্যবাদ জানাই, বিশেষ করে বঙ্গবন্ধু কন্যা মাননীয় প্রধানমন্ত্রী জননেত্রী শেখ হাসিনার যে ডিজিটাল বাংলাদেশ, সেই ডিজিটাল বাংলাদেশের যে অ্যাপ্লিকেশন, সেই অ্যাপ্লিকেশন রাজুকে ইতিমধ্যে আপনারা করেছেন। আর তার জন্য আপনাদেরকে আমি অনলাইনের মাধ্যমে যে আপনাদের যে শুরু হয়েছে, এই জন্য আইবির পক্ষ থেকে আপনাদেরকে ধন্যবাদ জানাই। আমি আমার প্রকৌশলী ভাইদের কাছে কয়েকটি আনন্দের বার্তা দিতে চাই। আমাদের কয়েকদিন আগে আমাদের বিশেষ করে ইন্টারন্যাশনাল প্রফেশনাল ইঞ্জিনিয়ার্স অ্যালায়েন্স যেটা হংকংয়ে হয়ে গেল, সেখানে আমাদের জাতীয় যে শিক্ষক আমাদের প্রফেসর ডক্টর জামিলুর রেজা চৌধুরী স্যার, আমাদের আইবির জেনারেল সেক্রেটারি প্রফেসর সাইফুল আহমদ দীপক কান্তি স্যার, আমারও যাওয়ার কথা ছিল সেখানে হংকংয়ে। আমাদের সেখানে যে প্রোগ্রামটি হয়েছে সেখানে তারা ওয়াশিংটনে তারা নীতিগতভাবে সিদ্ধান্ত নিয়েছে যে আমাদের যে প্রফেশনাল ইঞ্জিনিয়ার্সকে আমাদের আগামী দিনে পার্মানেন্ট মেম্বারশিপ দেওয়ার জন্য, যেটা আগামী বছর রিভিউ করার জন্য সেই পার্মানেন্ট মেম্বারশিপ পাবো। আর পার্মানেন্ট মেম্বার পেলে আমাদের প্রফেশনাল ইঞ্জিনিয়ার ইনশাল্লাহ আগামী দিনে চার্টার্ড ইঞ্জিনিয়ার বা সারা বিশ্বে আমাদের ইঞ্জিনিয়ার কাজ করতে পারবে বলে আমি বিশ্বাস করি। এছাড়াও আমি অস্ট্রেলিয়ায় গিয়েছিলাম, সেখানে অস্ট্রেলিয়া মানে ওয়াশিংটন অ্যাকর্ডের যে আজকের যে ভাইস চেয়ারম্যান এলিজাবেথ টেলর, তিনিও হংকংয়ে এসেছিলেন। আমি সেখানে বিশেষ করে অস্ট্রেলিয়ার যে ইঞ্জিনিয়ার্স অ্যাসোসিয়েশন, ইঞ্জিনিয়ার্স ইনস্টিটিউশন, তাদের সঙ্গে আমি আমাদের ওখানে যে ইঞ্জিনিয়ারিং চ্যাপ্টার আছে সেখানে চেয়ারম্যান ইঞ্জিনিয়ার মতিন, ডক্টর কামরুজ্জামান আমাদের সেক্রেটারি সহ আমরা বসেছিলাম। তাদেরকে আমরা বোঝাতে সক্ষম হয়েছিলাম যে আমাদের দেশের প্রায় 2300 থেকে 2500 ইঞ্জিনিয়ার সেখানে অস্ট্রেলিয়াতে কাজ করছে তাদের ন্যাশনাল বিল্ডিং এর জন্য, তাদের স্ট্রাকচার, তাদের এনার্জি সেক্টরে, তাদের বিল্ডিং সেক্টরে, তাদের রোড সেক্টরে। তাহলে আমরা বলেছেন যদি আমাদের ইঞ্জিনিয়াররা তোমাদের এখানে যদি 20, 25, 30 বছর কাজ করতে পারে তাহলে হয়তো আমরা কেন পার্মানেন্ট যে ওয়াশিংটন অ্যাকর্ড পাবো না। আর এই জায়গায় খুশির খবর যে এলিজাবেথ টেলর এবার এই হংকংয়ে সে চেয়ারম্যান হিসেবে মনোনীত হয়েছে এবং বিশেষ করে অস্ট্রেলিয়া ইঞ্জিনিয়ার্স অ্যাসোসিয়েশন তারা আমাদের ব্যাপারে হাইলি অ্যাপ্রিসিয়েট করেছে। আমরাও তাদেরকে আগামীতে তাদের সুবিধাজনক সময় বাংলাদেশে আসার জন্য বলেছি এবং তারাও আমরা আশাবাদী আগামী দিনে আমরা ওয়াশিংটন অ্যাকর্ডের ইনশাল্লাহ আমাদের এই প্রভিশনাল মেম্বারশিপ পার্মানেন্ট মেম্বারশিপে ইনশাল্লাহ আমরা রূপান্তরিত হতে সক্ষম হব, সেই নিশ্চয়তা আমরা ইনশাল্লাহ পেয়েছি। তাই আগামী দিনে বাংলাদেশকে 2021 সালে যে মধ্যমায়ের দেশ বা 41 সালে আমরা উন্নত বাংলাদেশের স্বপ্ন দেখছি, সেই স্বপ্নের কারিগর আজকের আমাদের ইঞ্জিনিয়াররা, যারা আগামী দিনের যারা প্রফেশনাল ইঞ্জিনিয়ার, যারা আগামী দিনের চার্টার্ড ইঞ্জিনিয়ার, তাদের হাত ধরে বাংলাদেশ এগিয়ে যাবে সেই আশাবাদ ব্যক্ত করে এবং ইঞ্জিনিয়ার্স ইনস্টিটিউশন সবসময় এই লেটেস্ট টেকনোলজিকে আপডেট করার জন্য, এক্সিলেন্স বৃদ্ধি করার জন্য আমরা সবসময় কাজ করে যাব এবং সেই কাজ করার জন্য বিশেষ করে আমার সিনিয়র শ্রদ্ধাভাজন ইঞ্জিনিয়ারদের আমাদের সহযোগিতা প্রয়োজন এবং আমরা সবসময় আপনাদের সহযোগিতা পেয়ে আসছি এবং বাংলাদেশ ইঞ্জিনিয়ার্স ইনস্টিটিউশন সবচেয়ে প্রাচীনতম প্রতিষ্ঠান হিসেবে আমরা বিশ্বাস করি। সারা বিশ্বে আমাদের যে মর্যাদা অনেক বৃদ্ধি পেয়েছে, আমরা এই মর্যাদাকে আরো এগিয়ে নিয়ে যেতে চাই এবং ইন্টারন্যাশনালি আমাদের এক্সিলেন্সকে তুলে ধরতে চাই লেটেস্ট টেকনোলজি আমরা অ্যাডপ্ট করে। যাই হোক, আমি আমার বক্তব্য আর দীর্ঘায়িত না করে আবারও আপনাদেরকে আন্তরিক কৃতজ্ঞতা এবং ধন্যবাদ জানাই, বিশেষ করে আজকের কিনোট স্পিকার যারা ডিসকাশনে ছিলেন আর বিশেষ করে আমার বন্ধু রাজুকের চেয়ারম্যান ডক্টর সুলতান আহমদকে ধন্যবাদ জানাই আর বিশেষ করে আজকের যারা আমার সামনে যারা আছেন সবাইকে আমার আন্তরিক কৃতজ্ঞতা এবং ধন্যবাদ জানাই আমি আমার বক্তব্য শেষ করছি। ধন্যবাদ।